So you're going to build an engine. What are you going to build it out of? You know? I don't know. That's just a thought I had.
Accumulated a few parts, give you some ideas.
Yeah. You know, these are some of the choices you have between a welded stroker and a forged stroker. And,
yeah. Well, why don't I get the liquid wrench out of the way here and just go ahead and let's start at the heart of the engine. Let me get this out of here.
We're done with that now.
We're done with that. And start at the heart of the engine, the crankshaft.
The heart of the engine is one of these three pieces here. We could actually start with showing even a stock 69 stroke crank that comes in the machine, but
most people have seen that.
Yeah, they've all seen that, and they've all got one. You know, if they're at this point, they don't need to see it. But both of these crankshafts are a welded stroker. You know, or you can even get this particular crank here is a 69 stroke. It's just got welded on counterweights. Okay, this crankshaft here is a welded on counterweight with a welded journal to extend the length of the stroke. It's offset ground after it's welded. Both cranks, excellent, you know, for what you're going to do with them.
And what's this beauty?
This is a new forging. This is a forging that's come from Bug Pack, I think. And it's a 82 millimeter stroke. And I think this one is a Porsche Journal. This is one of the first ones we've seen like this. We haven't seen any in service yet, but it's a really nice looking crankshaft. And it gives you a lot of strength to build an engine on, I believe. You know, there's a couple new forgings coming out now that are, you know,
but a crankshaft like this, I believe here in 1983 that a crankshaft like this runs around $500.
Somewhere in that neighborhood, yeah.
Five and up.
Yeah, and up. And a crank like this, a welded crank,
goes anywhere. A welded stroker starts anywhere from 150 on up to, you could pay $375, $400 for it.
Yeah, and they're both forged cranks.
They started out as a forging. This has had the journals welded to relocate them to increase the stroke. Okay.
So this is not a bad way to go then, if.
Oh no, this is the way we went for many years. Technology and engineering has produced this. You know, we've dealt with the Okrasas before. Okrasa always made a new forging in the form of a crank, anything from a 69 to an 84 millimeter. And they were very good crankshafts. They still are. This just happens to be made by somebody else now, and can be bought for a lot less money.
An Okrasa crank on the average starts at about $800.
Yeah, here in 1983.
Right.
Yeah.
This particular crank can be bought probably in the $500 range, and it will do everything that anybody wants it to. You know, there's going to be crankshaft failures. I don't care what kind you get. You know, depending what you do to it and how you take care of it. You know, connecting rod. You can start out with Old Faithful here. This is the one that Volkswagen came up with. And I say anything under 150 horsepower, this rod is more than adequate. You know, and I doubt very many people will argue with me on that. The next best thing after that, there's other things, don't get me wrong, but these are the things that I recommend, you know, is a Carrillo rod. It's in my opinion, one of the strongest rods. You can buy a titanium rod, but I don't even have one because I can't afford it. You know, a whole set of Carrillo rods today would sell for about $600, $650, and a set of titanium rods for a little over $1,000. You know, so there's quite a margin there that has to be dealt with strictly in the pocketbook, because this rod here is going to do everything the titanium rod will do. You know, this rod here, somewhat uncommon to the air-cooled Volkswagen people.
It's a water-cooled.
It's a water-cooled rod. This is out of a Rabbit, or a Sirocco, or an Audi Fox, or I don't know. Let's see what else would come with it. A Dasher would come with it.
And even
this rod has got a.
Chrysler made a motor with that.
Yeah, you could buy a Dodge Omni and a few other deals made by Chrysler that came with that particular engine in it. This rod is one of the strongest rods for its size around. This particular crankshaft here has had the journals ground to the same size as the standard Rabbit or Sirocco, what have you, water-cooled engine. Even an Audi 5-cylinder 5000 engine has this same rod in it. They've ground the journal smaller and offset it off of a 69-stroke or standard Volkswagen journal. This crankshaft ended up being, without any welding on the journal, a 78-millimeter stroke. Somewhat economical in a sense that you can get a long stroke motor with a readily available rod. And it can be done. We've done quite a few of them, you know.
Mm-hmm.
The hardest thing is to find a set of these rods.
Yeah, and as of today, I understand that these are available only in sets.
Only in sets.
From the dealer.
You
and,
also-
and they're quite expensive
Right,
too.
and you also have to reverse the bolt.
The bolt has to be reversed and a nut put on it.
Good point.
And-
But
yeah.
you can take this rod, take this 82-millimeter stroke crankshaft, do the same thing to it as we did to this 69-stroke, and get up to an 88-millimeter stroke
88.
By offset grinding.
by offset grinding that crank. So you can achieve something with a rod that's available, reasonable in price, and is strong. I think it's a good way to go, especially if somebody wants a real torquey
Mm-hmm.
street engine, or even an off-road engine. We've seen quite a few of them in off-road engines now.
Very beefy little rod.
Yeah, it's a very strong rod. After you get done with the connecting rod, you know, all these choices that we're talking about here are things that you should think about before you decide what kind of an engine you're going to build. Don't get halfway started and then just, you know, have a set of Volkswagen rods and then decide you want to buy a set of Carrillos, you know, or you want to go into something else. You know, plan this thing so that you don't end up with a whole bunch of leftover parts that you didn't use. You know, get advice, talk to people, and you'll find that in any case, the choice you make in the beginning, if you follow through with it, will save you money. You know, you won't be doing things twice and 3 times. You've got a crank now, if you've made that decision. You've picked the connecting rod, you know. We kind of overlooked it here. The case you have, if you've got a case that's, let's say you've got a 69 Volkswagen and the case is good. There's no cracks in it, you've inspected it, and you've had it checked, and it's clean, then there's no reason not to use that case. But if you have to buy another case, and you can't find a good used one that you know is good, then the next choice you have is to buy a new case. And today, this is the case you're going to generally buy. You can buy this case right now for, on the average,
About $325 to $375.
yeah, under $400. This particular case, if you see back here, Volkswagen had a tremendous tendency to crack right back here behind number 3.
Yeah, if the camera will come in here and take a look at this built-up thing, and you can compare it to your
Well,
other case.
Volkswagen did us one better, and they made the casting. This is a die-cast case. It's magnesium, and they basically filled this whole section in here, made this area much beefier, so that where the spigot that the cylinder seats in, right here, has got some backing behind it, so that when you bore it for larger cylinders, it's not going to crack. You know, there was other reasons that caused it to crack, and they also solved that problem too. The case is just superior to anything for the air-cooled engine short of a new aluminum case. A few people now are coming out with their own castings, you know, with an aluminum case to replace this case. The cost of them, I can't tell you what it'll be. You know, I'm sure it'll take more than a couple hours overtime to pick one up. This case here, in my opinion, for anything you're going to do is more than adequate.
If you're going to use your old case over again, or you're going to find a good used case, you better know how to check it for cracks, where to look for cracks, and you better know how to check it for warpage. Make sure the case hasn't been overheated and warped and that it's not cracked.
After you've decided on a case, you've decided on your connecting rods, you've decided on the crank, you're going to want to choose a piston and cylinder suitable for what you're going to do. There's good piston and cylinders from everything from 85.5 millimeter all the way up to, I don't recommend going bigger than 90 millimeter. You know, you can buy
90.5.
90.5s by Siemens. NPR makes a 90 millimeter piston and cylinder. The external dimensions of this cylinder on the OD is the same as a 92 on both ends. In other words, you could have a case and cylinder heads bored for 92s, and this will fit your case and your heads. But the inside dimension is 90 millimeter. The cylinder is much thicker, much more stable when it reaches operating temperature. It stays round. It doesn't draw itself square through the stud pattern, and you have basically a square cylinder and a round piston and a round ring in it. You know, this is what happens with 92s. There are other larger piston and cylinders available for these engines. The piston is a die cast for the 90 millimeter. It's a die cast piston. It's made by NPR. Probably for a die cast piston, it's one of the best you can buy. They come in a stroke dimension for a 69 stroke and an 82 stroke. Think about this before you build an engine. If you're going to build a 78 millimeter stroke or an 82 millimeter stroke, buy an 82 millimeter stroke piston. Okay?
That would be an NPR-B.
Right. NPR-B. You can also buy them in, I'm not sure if Siemens got them yet, in their 88s and their 90.5s in a different stroke length.
No, they don't. No.
Rumor had it they were supposed to, but I haven't seen them yet.
Well, we'll get in, when we get to the Siemens, we'll get into that.
Yeah.
They do have them in the 90.5s, but not the thick wall 88s.
Yeah, anyway, what it enables you to set the deck on the engine without using a spacer. And this is, I think, a tremendous advantage if you can do it. Okay? I still say that the NPR is one of the best die-cast pistons you can buy. Next step here is, in my opinion, the best for any use. This particular is a SEMA 88 millimeter piston and cylinder. There's a piston and a cylinder. The outside dimension of this is the same as a 90.5. Same reason as that. The cylinder wall is thicker. It stays round and retains its cylinder seal. The piston can stay sealed up in that cylinder at operating temperature and for a much greater period of time than anything else. Mm-hmm. The piston itself is forged. It's a forging. It's a much lighter piston. If you were to hold this piston, this feels like a brick compared to this. Depending on what you're doing with the engine, you know, can determine what you want to run with piston weight. Back to this. This has got a 2 millimeter ring, top, first and second ring on it. They're 2 millimeter faces. This has got a 1.5 millimeters each. 1.5 millimeters is a thinner ring. Higher RPM engines like thinner rings. Mm-hmm. You know, there's no way around it. This particular piston comes now with a thicker crown. In other words, the thickness of the top of the piston is greater than any of the other pistons you can buy. And if you get into having to notch the piston, this is something you want to take into consideration. Don't run a piston that when you put a notch in it, you're going to start cutting into the strength of the top of the piston. Mm-hmm. Like I said before, it's a forged piston. It can maintain more temperature, more combustion chamber temperature, and withstand more pressure than a cast piston can.
Okay. Yeah, now this SEMA is made in Brazil.
Mm-hmm.
The NPR is made in Japan, of course. And the company that makes this in Brazil is a very, very well-known and old-line German company called Mali or Mal, however you would like to pronounce it. And the other one, I believe, the COFAP, which is a Brazilian piston. I don't think you'll find it in the big bores so much, but that's made, the Kolbenschmidt.
Kolbenschmidt, right.
Is a German company. So these are made in Brazil. They've been coming out of Brazil for years now.
That's the only place this piston ever came from was Brazil.
It's beautiful.
It's a beautiful piston.
Also on the SEMA, as of very closely to the time this tape was made, SEMA now makes their 90.5 with the outer bore of 92. So that's a thick wall. The only difference in the 92 and the 90.5 compared to the 88 is on the 90.5 it has a 2mm ring, like the 90, and it's not.
I don't recommend a 2mm wide ring
On
for
an
a
all-
high RPM. A motor that's going to run over 7,000 RPM.
Street motor, they're fine.
It can't maintain cylinder wall pressure. It gets air between it and it loses its seal. And then you end up with crankcase pressure after about 7,500. You know, it's just not as efficient a combination. You mentioned Mala. This particular piston here, we're just going to whet your appetites out there. Any of you that buy this tape that understand anything about Volkswagens, you'll have to go take a cold shower after you see this. This is the spiral cylinder, as we know it. It's a cast iron liner with an aluminum jacketed fin. Now the two are cast together. You won't find a better cylinder made anywhere, in my opinion, in the world than this here for a Volkswagen. It's very light, very, very strong, and next to impossible to find anymore. They stopped making them, I would say, about maybe 1975, maybe 1974. I don't remember that well. The piston was a forging. It was made by Mala. This guy probably forgot more about making pistons than anybody in the United States knows. The ring configuration, it had a Dykes ring on the top. I won't go into what a Dykes ring is if you don't know. I'd just confuse you anyway. A 1.5 mm second groove, a conventional oil ring,
Slipper skirt
and a
design.
slipper skirt design. Now the thing about the slipper skirt design,
As
you
compared to a
can
full
compare to a full skirt.
Camera can come in and see this here, perhaps.
Full skirts all the way around it.
Full skirt.
Slipper skirts just on the thrust surfaces of the piston.
It reduced weight, and it also reduced the friction surface the piston could apply on the cylinder. And the structure of the piston, if you see these struts that ran across it here, kept the piston much more stable, and it maintained its clearance throughout all temperatures. Cold, it would have, let's say it had 2,000 piston cylinder wall clearance, and at operating temperature it had 2. That's something that, this piston is the next thing to this as far as maintaining that. But you get into some of your other pistons and that, it just isn't there, you know? And that's why this piston, you look real hard and real deep at anybody that's going real fast today, and they've still got a set of these somewhere, you know?
As far as in drag racing.
Yeah, in drag racing.
But these are pretty hard to find.
Yeah, they're next to impossible to find.
A set like that on the market today, brand new set, are going for $700 for 4 pistons and cylinders.
And I'd pay it tomorrow if somebody come in and told me they had them. Okay, now we've talked a little bit about our piston and cylinder choices we have. These are all choices you have to make yourself, and your pocketbook kind of has to make this choice also, you know. But if you stay with any one of these, or this, the 88 or the 90 millimeter, for a street engine, you know, I don't care how high performance it's going to get. Both these pistons and cylinders are going to give you the best possible combination for the street. If you went to the 90.5 rather than the 90, that's fine. You know, you're not going to gain or lose that much, you know. Ultimately, I say the 88 on the 90.5 external dimension cylinder is the best you could get.
It's the thickest, right?
It's the thickest cylinder, the forged piston, the best ring configuration, the lightest piston. It has more things in its favor than anything. So that'd be my first choice, okay? Now we get down into what makes this whole thing work. And you can bolt all this junk together and it's just a compressor. you know, but everything has to work off the heart of this, and that's the cam. Cam choice is something that we could make a whole tape alone just on cams.
Spend hours and hours.
And in my opinion, I have cams I like, and 90% of my feelings on cam is what I've run and how I've learned to make them work. Norris makes good cams.
Cam Dynamics.
Cam Dynamics makes good cams. There's a lot of good cams on the market. Engel, I personally have a preference to Engel, but that's because I've used Engel more than any other cam. And I've also been able to get as much or more horsepower out of any engine I ever built with an Engel cam. You know, I'm not saying you can't do the same thing with a Sig Urson or a Norris or an Iskandarian or anything else. But everything has to be made to work together, and we've always used an Engel, and I'll continue to use an Engel cam. But I'm not saying anything bad about anybody else's cam. I want to stress, don't over cam your engine, because a 110 Engel cam on your Zenith equipped 1600 worked good, that you can keep everything the same and go put in a K8, which is a lot more cam with a lot more duration, and expect it to work. You know, the cam is great, but you've just got everything else wrong around it. If you have a cam that doesn't have over 290 degrees duration and 450 thousandths lift, then there's a whole array of valve train that you would change automatically by not having a killer cam. If you had a cam that had 500 thousandths lift and 300 degrees duration, you automatically put a dual spring on it and a good chromoly retainer, and you might give some consideration to what you're going to do with a lifter. You know, all these things have a bearing on what you choose to do. But don't think you can outguess them, you know, by putting the biggest thing in the world in it, because you're just going to have something that doesn't work at all.
Okay.
You've pretty much decided what cam you're going to use. There's an array of lifters you can choose. You can go down and buy a genuine Volkswagen lifter over the counter at the Volkswagen dealer, which is, there's nothing wrong with it. It's probably one of the best ones you can get. We've had a tremendous amount of success with the Wiseman one-piece lifter. It's not a pretty lifter. It looks like that. It's black. This is a one-piece lifter I've got in my hand here that's been modified. It's been made lighter, and the diameter of the contact surface of the nail head of the lifter is smaller.
Is there any particular lifter you should look out for that you don't want to use?
There are some lifters. I've seen them. They've got a marking on them there because they say POV, P-O-V, I think.
Is that a cast or a
Is it
cut?
POV? It's a cast lifter, but I haven't seen any of them really, you know, break any records. The experience we've had with this lifter, the Eaton lifter, which is, I think that's what this was originally, the Eaton lifter, a genuine Volkswagen lifter. If you buy, let's say you buy an Engel cam and you buy a set of their lifters, you're going to buy an Eaton lifter. Okay? In any case, never use your old lifters over again. Don't use a reground lifter. Always use a new lifter. And if you're in doubt as to what you're going to get for a lifter, either buy a genuine Volkswagen lifter, a Wiseman lifter, which is a German lifter, or the Eaton lifter. The Eaton lifter is almost identical to the Volkswagen lifter.
The Wiseman lifter comes in a familiar brown box.
Yeah, very common. Okay. Depending on the cam you use, this particular spring I've got here in my hand, this is a dual spring. You can, anything over, I say 290 degrees duration, you should, I can't get that off of there. You should put a dual spring on. It just keeps the valve train oh, I'm sorry, Gary. I just stabbed him. I got it. Anyway.
Oh, broke it.
The dual spring,
Cracked.
after a certain point in lift and duration, keeps the whole mechanism tracking the lobe of the cam. As it comes out over the lobe, it wants to come back. The spring wants to push it back. If you don't have enough spring at the RPM or high RPM, it wants to stay out there, and it causes, you know, what's very common to everybody as valve float. You don't want that. So after a certain point, your cam grinder will recommend, after a certain point, what spring you should what you should use for a spring, a single or a dual. I personally, after 290 degrees duration and 450 thousandths lift and above, I say a dual spring is a must. You can get into, in a real high performance application, this particular retainer is titanium.
Titanium retainers.
They're very expensive, but it eliminates a tremendous amount of valve weight.
It didn't crack.
No, it didn't break. I don't think it will. The titanium retainer, a set of these retainers are about $22, and a set of these are about $60. But they're stronger and lighter, and weight is a factor we want to try to eliminate in a real high performance engine.
Is there ever a danger of, let's say someone doesn't build a particularly large engine, is there ever a danger of putting on too heavy springs for the particular application?
I would never use a dual spring on a stock exhaust valve, especially if you intended it to be used every day, day in, day out. The stock exhaust valve.
No matter the cam or the stroke?
Well, anybody that, I wouldn't build an engine with a stock exhaust valve that was going to be a high performance engine anyway. We have people that come in and they want to put an Engel 130 cam with stock heads. So right away we try to deter them. There's no reason to mix match all these pieces. So you try to back them up a little bit, put them into a 110 rather than a 130. But that's just the thing I was saying earlier. Everybody wants to over-cam it. They've got a set of 40 Weber carburetors, a 1600 with a 110, and then they think, well, I'll just put a 130 in it, and I'm going to go beat all my buddies on the street. Well, this won't happen. All he's going to do is break the exhaust valves off, beat the keeper grooves up, and probably suck the retainers right through. So there's a time and place for everything whenever you're building the thing, building the motor. The rocker arms, you have a lot of choices in rocker arms, and depending on the cam you use will determine what you're going to use for a rocker arm. In the particular case of the cam grinder or the design of the cam you buy will determine the rocker arm right off the bat. In, I'd say, 70% of all cases, you'll use your own rocker arms, your stock rocker arms. This particular case, here's a set of, these are stock 1.1-to-1 rocker arms right off of a 1600 Volkswagen. More than adequate in strength for any cam designed to use a standard rocker arm. You may change the adjusting screw depending on the valve you use, but the rocker arm is more than adequate. You also may change the shaft. You might put a hardened shaft and a spacer kit and lock nuts such as these here, and you'll have yourself as strong a valve train or rocker arm system that you can get. That depends on whether you choose a cam that uses a stock rocker arm. In the case that you don't, let's say you buy an Engel K8 or you buy a Sig Urson, I'm not familiar with their grind numbers, but a Sig Urson cam that required a ratio rocker, a higher ratio rocker, to maintain the lift they design into the cam, you'd buy, or you can get
the Sig Ursons you're talking about.
the Sig Urson rocker arms. These rocker arms change the ratio that the valve opens against what the lobe of the cam makes it do. These rocker arms here, if you bolt them on a stock cam, will increase the lift, but not the duration. Very common. These have been around for a long time. They're in a very low performance application, they're great. If you're going to put them on a cam that you're going to try to get over 500 thousandths lift out of, then they need some modification. You know, they're not adequate as they are, as they're sold. You can try it, but I can guarantee you'll be bringing them to somebody to put bushings in them, or you'll be replacing them with something else later. This here is an old standby here. This is another item that's next to impossible to find. This is a EMPI 1.4 to 1 ratio. By the way, the ones I showed you here that were Sig Urson were 1.5 to 1 ratio. And this here is an old EMPI, even says EMPI on it, look at that. 1.4 to 1 ratio, and they've been around for many, many years. In fact, they're next to impossible to find now.
You might want to...
This particular rocker arm here is a Gene Bird rocker arm, new one. And it's a 1.5, let's see, what were the ratios that he advertised?
1.53.
1.53 ratio and a 1.45. And in both cases, these ratios were established off of a stock cam. So after the stock cam, the ratio starts multiplying itself. And under no circumstances, and I'll recommend it right now, and if you're listening, take heed, don't buy the 1.53s. For anything other than a stock cam. You'll end up with more lift than your valve springs or your cylinder head or anything can accommodate. The 1.45 is fine. It's perfect. But the 1.53s are what happened or why it ended up that way. I've seen it, I've had them, and they will not accommodate. Like an FK89 angle cam, there's not enough room to open the valve. It gets so dramatic. You know, it gets so, the lift just starts multiplying to the point where you can't. The Sig Urson rocker on an FK89 cam will open at approximately 580 thousandths, and that's a 1.5 to 1 ratio. The 1.53 ratio, as advertised, opens that cam almost 700 thousandths. There's no way that a Volkswagen head will accommodate that much lift. The strongest rocker arm on the table, I will say, is probably the Berg. Then I would say the EMPI or the Autocraft, then the Urson, and the stock's probably stronger than any of them.
But for its application.
For its application, it's limited. Okay. Yeah. Cylinder heads. This is the point everybody wants to know about. It's probably where you'll put the most amount of money in your engine, you know, aside from the pieces that rotate and hold it together on the bottom. There's so many choices of cylinder heads around, it's not funny. There are more people making cylinder heads now than ever.
Okay, yeah, we'll hold this up and then you can show it on the camera a little bit. Let me get out of the way here so that you can take the center of the table here.
Okay. When you start to build your engine, if you've given thought to using anything we've talked about here so far, you're going to want to at least install big valves and port cylinder heads and reshape and redesign the combustion chamber for better combustion, better flame travel, and, you know, change compression ratio.
Move this out of the way so you can just move it over here.
Okay.
That'll be fine.
In this particular case here, this cylinder head is a highly modified Volkswagen head. Started out as a Volkswagen head, probably made about, or the same design since 1967 on the Type 3s. It's a dual port head. It's been extensively welded up here, through the center here. It's had aluminum silicon bronze valve seats installed in it. This cylinder head here on a 1800cc engine will produce over 200 horsepower. The same head on the same size engine with a different cam will produce less horsepower, or with a smaller cam and less compression. Okay? There's a couple things that determine the horsepower an engine can produce, and that's the compression ratio and the carburation and the cam you choose. You could take the same port design and change those other three factors and have a whole different engine. So when you're building your engine, take into consideration what you're going to do with it and where you're going to use it when you decide on those three factors: compression ratio, cam choice, and carburation. Everybody wants to run a 2180 with 48 Webers and the biggest valves possible, you know, and the biggest cam possible. Doesn't always work that way. This particular head, this has got 14.5 to 1 compression on an 1800cc engine. Not quite what you'd like to drive to church on Sunday. But in a quarter-mile drag race car, it's really, you know, the minimum. You know, might even like to have a little bit more compression than that. The average street engine, I would say, should have at least a 40 millimeter intake valve and a 35 millimeter exhaust valve. And I think that the choice of valves is a good stainless valve. I try to stay with Manley valves. This is a 40 millimeter intake and a 35.5 millimeter exhaust. And depending on the engine you build, this is just about where you want to be. You can go to a 42 millimeter intake and a 35.5 millimeter exhaust, but when you go to the 42 millimeter intake, you start running into the spark plug with the valve. So you have to move the spark plug. That can start getting even more expensive. So stay with your 40 and your 35.5 under normal situations. And if you start really wanting to squeeze it, then you can go to your larger valves. But take into consideration that you're going to have a lot more money in your cylinder head before you get through. If you really want to get exotic, you can put titanium valves in it. And this is a titanium intake and exhaust. This is a 42 millimeter intake and a 37.5 millimeter exhaust. These particular valves cost about $50 a piece. So it's not what you want to. I don't recommend them for the street. If you're going to build strictly a drag race engine and you're real serious about it, then I might give some thought to these. You know, I brought them out here more for the comparison in size more than anything else. If the camera can come in, you can see the difference in the dimension there. That's the 40 against the 42. And this is a 35.5 against the 37. So there is a noticeable difference, and a noticeable difference in performance when you compare the two. The cylinder head, I doubt very much whether a lot of people are capable of doing their own or building their own or modifying them themselves. I recommend you find somebody that does it professionally, and upon you deciding to have them do your cylinder heads, demand that you see something they've done before. Don't just walk in and take the guy's word that he can port cylinder heads and weld them and install seats and do a valve job. Everybody says they can do that. Tell them you want to see some of their finished work, you know, so that you can judge what you're paying for. And check around. There's a lot of places that are doing heads real cheap, and you're getting what you pay for. I personally think that a good set of street heads should cost anywhere from $650 to $1,000, you know, for a set of heads complete. And the difference between $650 to $1,000 depends on what size valves you choose, what size port, and what type of manifold you use. This manifold right here is a tall manifold for a 48 Weber. And it's been ported and matched to this head. There's the carburetor. And for the optimum, this is what you want for the street. You know, this is the top of the line for a street engine, for a fast street car or all-out drag car. They're kind of a pain in the neck to live with on the street, especially when you have to put gas in it and pay for it yourself. but that's the state of the art. You know, that's the top of the line. This particular manifold is for a 40 millimeter IDF Weber or a 44 millimeter IDF Weber. It's a smaller, shorter manifold, excellent for the street. Makes a very drivable, tunable, good gas mileage, if everything else is in tune to gas mileage. Combination. The carburetor is as tunable, if not more tunable, than a 48. Not an expensive carburetor, and will deliver good performance along with good economy. We've actually seen increases in mileage over this over some stock applications, you know.
Why don't we go through the rest of the carburetors while we're on the subject? Real quick.
While we're on the subject of carburetors, there are other carburetors available. This particular carburetor is a 40 millimeter DCNF3. They also make a 42, and there are rumors there's a 44 around. I would stay away from it if possible. The 4042 is a good street carburetor, not optimum performance. You know, if you're looking to build a real stout street engine, this isn't what you're looking for. But it's a good middle of the road dual carburetor setup.
Mr. Zenith.
Mr. Zenith, this is Old Faithful here.
Yep.
I don't recommend this in a dual carburetor application, but everybody I know that races off-road somewhere along the line has got one of these back on the shelf. It's probably one of the most reliable carburetors money could buy.
It's also good for the street.
It's a very good street carburetor. It's an economical carburetor. It's a little bit expensive today. In fact, they're almost ridiculous. But if you run across one and it's in good shape and you want to run a single carburetor, don't hesitate. They're a very good, very tunable carburetor. This is something that's kind of new on the market. I shouldn't say new. I've seen it for the last 8 years or so. This is a progressive Holley Weber. There are also some progressive Webers. They vary in size. This carburetor made its debut on Pintos and Vegas, and then kind of got resurrected into the Volkswagen. But it's a very economical, yet it does give more performance than a stock carburetor. And it's because by progressive, I don't know if the camera can come in here and show this. This is your primary venturi, this is your secondary venturi. The primary opens up almost 2/3 of the way, or 3/4 of the way, and then the second venturi, or throttle valve, opens up. And that's why they call it progressive. And what it does is when you're just driving around and you're not really looking at the performance end of it, you're using just this front venturi, or this throttle valve. But when you need the added performance and you come down on the throttle, it opens the second one. So you get a little bit of your cake and eat it too with this carburetor. It's economical. You can take that carburetor and with the right minimum changes in the motor, let's say a 1600 or 1700 cc engine with stock heads, the smallest angle cam they make, with that carburetor and stock compression ratio, you can double the horsepower of the motor. We've done it many times. And have it last. Nothing to have that carburetor run and the motor that it's underneath or that it's on top of give the same service as a stock engine, and at twice the horsepower. So
you don't have any Hollies back here.
Well, they cover enough of that in that book they made. How to hot rod your Volkswagen.
Well, there still are a few Hollies floating around.
Oh yeah,
that's where they should go, is float around. Right?
That's where they should float in the ocean. Anyway, cylinder head wise, like I said, you've got a million choices. Carburation, there's a million choices. If you're in doubt, ask questions. Now we'll get up into a little more exotic cylinder head here. This is ARPM's Superflow head. It's being marketed by, I don't know,
Bug Pack.
Bug Pack is doing the best job with it so far. And in my opinion, it's going to be hard to beat. I have personally flowed some. If you notice back, I think we used one of these in a flow test.
Yeah, we could show a little bit of it now, too.
Right.
On the flow bench.
And you can see that it's better than your average head, especially for buying it off the shelf. The material it's made out of is excellent. The casting is, you know, hard to beat. It's there. It will bolt right on. Everything will fit it. Your rocker arms will fit it. You know, it'll bolt right onto your motor. I don't suggest putting one of these on your 1600. It's too big. You know, I would have at least a 1800cc motor or bigger before I start using this head.
Well, they're also coming out with a...
Yes,
Yeah, they're supposed to come
They
out
told me down there that they're going to come out with a stock
with
16
a smaller
Superfly.
Superflow head that'll better serve the needs of the smaller engine.
Yeah.
You know, and I think this is what we're going to see more of in the future, and time will tell how it works. I personally haven't seen any in service on the street yet. This is a counterweighted forged crank right here that's going to start being installed in a motor that we're going to watch go together from stage one, you know, almost from the time the customer called and said, this is what I want, all right? And maybe we can convey some of the things to watch out for, the things that are going to be needed to do when you assemble a motor like this. You know, there's a lot more things to watch out for. Clearances, because the engine's going to see more RPM. We're going to want to see less clearances in some places, tighter clearances in others. The strength of the parts you use are a lot designed, you know, it comes from the fact that you want this thing to do a certain job. If it's gonna produce 150 horsepower, you can take and install a Volkswagen rod in it with not really a lot of trouble, you know, and it will give you good service. It will last, you know, a reasonable amount of time. A motor that's going to see 200 horsepower and be nothing but drag raced, I would like to see something used in the form of a Carrillo, a rod like this, and you're looking at a lot of money, but it's something that is going to reward you in the end. You know, this rod here is only good for so much. This one's good to the end.
This other rod was just a stock Volkswagen rod.
Yeah, this is a stock Volkswagen rod out of a 67 and later engine for all practical purposes.
Pretty good rod though. Really.
Yeah, it's a magnificent rod. It's, in my opinion, there's probably not a better rod designed for its uses, you know. And for the average guy at home that's going to build a hot rod street Volkswagen, this rod is the ultimate, you know. And we won't dwell on this rod very much, only in comparison to certain clearances, you know, and the fact that it's going to be stronger.
And in an all-out race application, the Carrillo rod gives you the peace of mind where you know it's going to be there. You know, granted, if you don't put it together right and you don't follow, you know, basic tolerances and clearance things, you're not going to have any failure out of that rod.
Something that should be said now, before we get much further into it, is that a high-performance Volkswagen engine doesn't need to be a 2180. You know, it can be a 1600. It can even be a 1500.
You mean I don't have to bore it out or stroke it?
No, it's not. You won't see the ultimate end, but it's not unheard of to see as much as 100 or more horsepower from a 1600. You know, granted, the larger you go with the motor, with respect to reliability, you're going to see more, a broader torque range, but you're going to spend more money to get it. You know, a 1600 with the right cylinder heads and the right cam and the right carburation can give you a real easy 115, 120 horsepower. You know, you can build an 1835 with 92s, which I don't really recommend. You know, 88 millimeter, 90.5, these are fine. The cylinder wall is of a design that can stay round and keep cylinder pressure and give you some kind of results, you know, over a long period of time. So I won't say a lot about it now, but
Yeah, well, that's usually the cheapest and easiest and quickest way to do it. That's
Right.
why most people choose it.
when they're new, they're fine.
And most people go, if their first instinct is to go with, if a bigger is better, a little bit bigger is going to be even that much better. It's not true, because you lose efficiency through what you lose with the size and the cylinder wall.
Yeah,
Granted, when you put it in, you first start it up, it's going to work real good.
yeah.
But a couple thousand miles down the road, you're going to lose a little.
And I like the smaller motor.
Yeah, the smaller motors seem to make every bit as much horsepower as the big motors, and you don't have to, in fact, maybe even a little more.
They seem to be down in up in the RPM range, I mean to say. I've been told by Dick Nuss that they work, and I doubted them for a while. I don't doubt them anymore.
No, seeing is believing.
Right today I'm running one of their old motors, and
That's the one that they've ran actually in their A car into the 30s and 40s,
right,
isn't it?
yeah, they same exact motor.
Very, very competitive.
Yeah, it's a fast motor.
That's what, 1700?
1700 cc.
1700 cc's.
102 cubic inch.
In a high performance engine like this, this engine is going to be, this particular engine is going to be a 74 millimeter stroke by an 88 millimeter bore. It's going to be a all-out drag race motor. Now, there may be a few things that you're going to have to back off on a little bit if you're building an engine that's not going to be a drag race motor, but a lot of the theory will apply. A lot of the setup in the motor will be identical to if you were building a 69 stroke by 90.5 with a good set of street cylinder heads. The clearances throughout that motor will be pretty close to the same. You know, you're going to rev it up a lot more. You're going to want more side clearance on the rods. You're going to want maybe a little bit looser clearance on the bearings. You know, it's never going to last as long as a stock engine. Don't ever think it will. You know, there's no way it can. So on this particular crank here, with this Carrillo rod and a stock rod, it's evident there's only about a thousandth of an inch difference in the side clearance or the thrust clearance of the rod. In this particular case, we'd like to see the thrust clearance not less than, I'd say 7 or 8 thousandths, and not more than 17 thousandths. In this case here, the Carrillo rod comes up with a side clearance or a thrust clearance of 12 thousandths, where the stock rod, because it's not meant for quite as high performance, it drops back down into the 10 thousandths range to the clearance of the rod in here. And you don't want to have this too tight because there's no escaping for the oil, and it pressure locks itself and then gets hot. The oil has to flow away from the bearings in order to remove the heat.
And when this crankshaft's spinning in there at 4,000 RPM or whatever, the oil that's coming out here is being spun in a huge circle, and it goes right up into the pistons and liners.
Right. It lubricates the cylinder walls, the wrist pins, even helps lubricate the cam.
Now, if you have too much clearance,
25 thousandths probably wouldn't hurt, you know, even in a stock machine. The thing it tends to, every time the explosion takes place in the cylinder, it forces that rod to one side or the other and creates noise. And it will create wear, ultimately. There is good lubrication there, so it's going to take a while, but it's not going to get better. It's going to get worse, and you'll have a noise factor, you know.
so side clearances are very, very important.
It's very important in respect to too little or too much. It's got to be right. You know, that's why we're saying it should be between, in a racing application, I wouldn't like to see less than 10 thousandths. Now, you may find people that'll disagree with me there, but I found the best bearing life I found in our own racing engine that, you know, 10 to 12 and even up to 15 thousandths doesn't hurt and hasn't worn anything out yet, and that's where I'm going to keep running it.
But a new 1600 crankshaft and rod, what's the average clearance there? Is there an average?
Yeah, about 7 to 10 thousandths. you know, which is plenty adequate because the motor never sees more than about 4,500 RPM, you know. And this particular engine is going to start producing good horsepower at about 6,000 RPM and continue to produce horsepower up above 9,000 RPM. So we're dealing with, we're out of the range of the stock engine, you know, which makes it kind of hard to believe this thing will withstand those kind of, you know, pressures in RPM, but they will if they're assembled right and have the right clearances.
This is a beautiful crankshaft. It's really a nice piece of machinery to look at. Well, what are the different crankshafts that are available to you?
Well, the basis for a good engine, in my opinion, is a good forged stock Volkswagen crankshaft. There's probably not a better forging made than that crank. There's welded on counterweights. You have a choice of cast iron cranks, which I don't recommend, especially in a high horsepower application. You know, they.
So you'd have to specifically say when you're talking about crankshafts, how is the crankshaft made? Is it cast or is it forged?
I would. A crankshaft should be forged, in my opinion, for a high horsepower application.
Well, let's back up. You're talking about an all-out race motor. If you're building definitely high horsepower, high RPM motor, a forged crank is definitely the way to go. If you're building, you want a good reliable street motor, we recommend that you go with either a forged crank if you want to put the money in it, or to a welded stroker, which becomes, it is a forged crank to start with, they weld the counterweights on. This particular crank, this is all the counterweights and everything is forged in one piece.
I think right over here we have a welded stroker there. Grab that over here and we can compare the difference.
You'll be able to see the difference.
You can see the weld line on it, and there's not a thing wrong with the comparison of these two cranks right here. Let's see if we can't get it so you can see the fact that it's welded on.
Right in here.
Yeah, right in here, right here. This whole counterweight is actually welded on, and in order to change the stroke, they actually weld the journal outwardly from the center and then regrind it back to standard, and it changes the stroke. The stroke is the distance the piston travels down and up the cylinder, and from the center line to the journal here is half the distance of the stroke.
Put it back on top of here and show them that basically in making these two cranks, all of this material here was forged onto this crank. Where if you look up here at the counterweighted crank, this whole counterweight you see sticking off here that looks like that has been welded onto it. The actual crankshaft they started with was a forged crank.
A stock Volkswagen.
It was a stock Volkswagen crank, and they welded the counterweights on it. It does stiffen and make the crank a lot more rigid for flexibility through the RPM range. And going back to, I think we should come back to picking a crank for what you want to do. We recommend in a very high horsepower, high RPM application, a forged crank is better. Your next choice would be going down to a welded stroker, which is a forged crank with just the counterweights welded on. We're not saying you can't use a cast crank, you know, which is, you know, normally just a cast iron crank or sold that way. Fairly inexpensive. They are cheaper to make. They aren't as hard. They don't have the wear tolerances or abilities in it and whatnot. They don't tend to last as long, and if you do start to use them in a higher horsepower, you're going to see a lot of problems. You can go into that a little bit with the dowel pin.
The tensile strength in a cast crank is not that of a steel crank, and the dowel pins that hold the flywheel on, if you rev that motor up to 7,500 RPM and dump the clutch, something's going to break. And it's generally going to be the flywheel coming off the end.
Show the dowel pins. It's just, you know, we're not saying not to use it. We're not telling you. We're trying to give you a basis as to what is better than the other and to pick the best application, like Dick had outlined earlier. Getting what would work best for your application.
You know, the size of the motor has to be determined by the size of your pocketbook a lot of times, because A stock 69 stroke Volkswagen crank with welded on counterweights, costs about $150. And will actually do the same job that a forged 74 or 78 or 82 stroke crank will do in the form of reliability. It's just that the physical size of the motor, the difference right there is going to make a difference in the horsepower and the torque curve in the motor. This is something we'll talk about later when we get into what different size motors can do for you.
And I think you can also mention of having it wedge mated.
Wedge mating is a process of holding the flywheel on that
Takes
it's
it
an
one-
interference
yeah.
lock between the flywheel and the crank, that when the flywheel is pulled up with the gland nut to the torque it needs, it actually interferences the flywheel over the end of the crank and almost makes them become one. And if you're going to drag race your car and you got in the neighborhood of over 175 horsepower and you use slicks on the car, this is a good way to go.
Right.
It's not imperative, but it's a good, safe way to keep the crank and flywheel you've got in one piece.
Well, it's in basically saying if you're building an all-out drag race motor, wedge mating is definitely something that you should do.
We're going to go on from here and take this crank and we're going to put the rods on it and we're going to lay it in a case and show where this stroker crank interferes in the case, where it has to be clearanced. Now, some cases vary. Your case might be able to take a 74 stroke crank without clearancing, but by all means check it. We're going to show you how to check it, the places to watch for in the case. You may see that our case doesn't hit where your case does, or where your crankshaft hits in your case. Might not be exactly the same, but 9 times out of 10 it will be. So pay attention and maybe take a few notes so that when you're out in the garage and you're not looking at the tape, you can check these places. We've put these rods all on the crank, and we put the crank in the case. Now, sometimes it's easier with them on and with them off if there has to definitely be clearancing. In this case here, we want to show where everything's going to run into each other. One of the most important things to check first, because it isn't always obvious, is that when the crank is pulled up laterally up against the thrust bearing, that there's ample clearance on the webbing of the crank.
Shows the webbing on this and
Okay, the webbing on the crank against the webbing in the case. Okay? Aftermarket cranks especially tend to be a little thicker in the webbing and they may interfere here. There's differences in cases and cranks, so it's a place to be careful. Look for a problem there. You might not have it, but check it anyway. If it's good, then go on. Okay? The next thing is the rods are going to run into the case. As the crank spins around in the case, the rods are going to come around and hit the case. One of the most obvious places is going to be at the top of the case, here, where the rod comes in. It's going to, all 4 rods are going to do it. It's going to interfere. There's going to have to be clearancing done here. The other place is down in the bottom of the case, on the opposing end of the rod, at the cap of the rod, is going to run into the webbing in the case, right through where the case savers come back in. On all 4 rods, opposing sides. Okay? The rod nut itself is going to run into the case directly in the middle of the spigot hole, top and bottom.
yeah,
Okay.
right in here and here. Huh?
Right.
Yeah.
On all 4 cylinders.
On both sides.
Both sides, everywhere. These places have to be clearanced. When the time comes for this, take it somewhere where they have the equipment to do a Volkswagen case. Another area is the cam. Anything much over 74 stroke, 74 millimeters of stroke, with a Volkswagen rod is more than likely going to interfere with the cam. The most common place is on the center main journal of the cam, about 3/8 of an inch in. The cam has to be turned down in its diameter just about the diameter of the casting of the cam.
Mhm.
You know, that diameter up here about 3/8 of an inch. On the thrust side, the back side of the thrust of the number one bearing there, or the bearing by the gear, has to be cut here. Now, this is something that just about any machine shop could do that has a lathe. You know, it's a very simple operation. There are other methods to do it. We'll show you different methods of cam clearancing, depending on the stroke and the motor.
Well, we will also show you cams that have already been
Yeah.
clearanced in the two
Right.
spots.
It'll be a little clearer, but right now we're trying to get it understood where to look for problems. You may have a 74 stroke with a Volkswagen rod, and it might not hit it, you know, but check it. Don't leave a question unanswered. You've spent too much money on the parts you got in this motor to waste them the first time you try to start it, or not even get it started, you know.
When you check clearancing, let's say you've done all the machining and you think you have it clearanced. At this point, would you mock the engine up?
Definitely so.
Uh-huh.
Just assemble it with a little assembly lube, put the rods on it, the cam in it, the crank gear, the bearings, put that case head together, and rotate the motor through quite a few cycles.
What would you go so far as to taking the rings off the pistons and putting
Yeah.
them on the pistons in the barrel?
We'll cover that when we set depth,
Oh,
okay?
all right. Because
there is a possibility, depending on the piston you use, that you may have to clearance the piston. Below the pin boss may need clearance, and even the cylinder might need clearance if you get into some longer stroke motors, depending on the design of the piston, who made it. Okay? I think we've pretty much covered everything that the cam or the crank is going to run into, except for the lifters. Okay? Now, I'm going to take this crank out of here, and I'm going to set it aside, and we're going to show you where to look for a problem. It's going to be a real common problem. Start to assemble a motor. And even in the case of a completely stock stroke motor, if you have other than a stock camshaft, this is one thing you want to definitely check. You can do it without putting the case halves together. You can do it, you know, all you have to have is an old set of cam bearings and the cam you're going to use. Bill got us some lifters here, and easiest way to do this is just take whichever lifter you choose. In this particular case, we're going to use a Wiseman lifter. It's a German-made lifter that, I'd say 9 out of 10 times, will give you all the service you need.
That's a cast lifter.
It's a cast lifter, but we found it to be very durable, and it's lasted in a lot of engines that have, 7 to 9,000 RPM range with dual springs and a lot of lift on the cam, and they give good service. Okay, what we're going to check here is when the cam is seated in its bearing again, and the lifters are in their holes, okay, and the lifter bosses, just rotate the cam around. And we've got a problem here, we can see it. The nose of the cam, or the lobe, comes around and actually interferes, you can hear it, with the face of the lifter. Okay, now what this tells us is that the lift that's in this cam, because it's not a stock cam, it's got more lift to open the valve further, it's running into the lifter. Now, if this were a stock engine, we wouldn't have this problem, but we're not building a stock engine. So, rotate it around. We know, okay, that one hits. The next one hits. You got one that doesn't hit over here. Okay, don't ignore it. When you take this apart, you might mix up the lifters, and they might not be exactly the same, and they could give you the problem again. Okay, what we'd like to have is about 30 thousandths clearance between that lifter and the lifter boss.
Yeah, when the lobe is straight down.
When the lobe is straight down. Okay, we have to allow for some valve float in the motor. In this particular motor, we have to allow for even more, but 30 thousandths is a good rule of thumb. Now, what we'll end up doing is the lifters have to go deeper into the case. We've got a tool that comes in and cuts this surface and rechamfers it. And depending on how much it interferes, we cut that much out and then give it its clearance. It's very simple, and it's something that you know you're going to have done. When you take your case to have it clearance, or if you send it to us or to anybody else, specify you want the lifter's clearance, okay? And they'll spot them off, chamfer them, and by no means, I don't care who did it, even if I do it. When you get it back, check it. Don't assume that anybody did it right, you know? And if it's possible, when you send the case to have this done, send your cam with it. So, and the lifters. They can check it for you right then.
And the cam manufacturer won't tell you that you need clearance here.
They very rarely know it. You know, they don't see the case. You know, they've got a room full of people grinding cams. That's all they're doing. You know, they know what the cam has to do.
They make cams, they don't assemble motors.
Right.
Yeah. But that's one of the things that you really want to watch out for unless you're using a stock cam. You know? So that's pretty much it on the clearancing. We'll show a case a little later that's had all these operations done to it, and we'll show you how it was done.
Double thrusting the cam.
Okay. On a motor that's got dual valve springs and a lot of high RPM, the thrust of the cam, this surface here, this flat surface here and here, rides up against this surface of the bearing. Okay, and the standard cam box of bearings comes with only half of the one bearing for the thrust. Now, what we recommend is that you buy 2 sets of cam bearings. You know, they're not expensive.
So you have two shoulders.
You have 2 shoulders. You have a full face across that. You don't just have half of it. You would insert the other cam bearing over here. They'll stay put. There's enough pressure on the bearing not to concern yourself with the bearing spinning. Okay? There's no locking tang or anything like that like the rest of them have. But don't worry. You can, if you really feel like it, in the side that's got it, you can put a little dimple in it right up here where the pointer is, and it'll maybe give you a little peace of mind. But I wouldn't stay up night worrying about it. But you will double the life of the thrust, and when you run a heavy valve spring, a stock valve spring has in the neighborhood of 50 or 60 pounds pressure on the seat, and a dual spring has about 140 pounds pressure on the seat. And when you're running that cam around, it's trying to open that much more weight, so it applies thrust because of the bevel cut gear. You know, it's trying to drive that cam this way, okay, or this way, you know, depending if it's opening the valve or closing the valve. So these are things that'll just help keep this high performance motor alive a little longer, you know, cut down on a little noise.
we got the clearancing. We've talked about the cam. We've talked about the crankshaft. These super special rods that we have in here now. I'm going to let you take it over from here, and let me get out of the way, and you can talk about what we have set up right here.
Okay, we've clearanced this case to take the longer stroke. We've gone back and taken the rods out that we started with, only because this engine, when it's through, is going to have these Corilla rods in it. We started out showing you the clearance that a case needs with a Volkswagen rod. You know, the average guy at home isn't going to step up and buy a set of Corilla rods, and I don't blame him, at $600 a set. In this case right here, we'll show what the end result was on the clearancing, and you'll be able to see a little closer what we did. These were the areas, we'll hold it up like this. This area up here was the area we talked about clearancing. In the top of the case, in the spigot of the case, and in the center webbing of the case. Now this has all been taken care of in this case, and the crank rotates, the rod's clear, everything is fine up to now. Now we're going to put pistons and cylinders on it, and because it's not a 69-stroke engine, it's a 74-stroke engine, or in whichever the case may be, it might be an 82-stroke engine. The deck height of the piston in the cylinder, as I bring this around, we'll try to get up here and show it, is, well, we're going to show them how to dead stop it, so they know that if their pulley's correct or not. But deck height is the distance from the top of the piston to the top of the cylinder. You know, depending on the RPM of the motor, the type of rod in the motor, and the compression ratio in the motor, designates what this deck height should be. Under no circumstances, it shouldn't be less than 40 thousandths or 1 millimeter. You know, and you can alter this deck height by either cutting the top of the piston, and or the bottom of the cylinder, or by accommodating the base of the cylinder with a shim or a spacer. There's a number of different ways you can do it. If it's at all possible to do without a shim, I recommend it. You're just asking for a possible leak with a shim. And in this particular case, because of the design of the piston and the cylinder design and the length of the rod that we're dealing with, we probably won't have to use a shim. You know, it's going to come in pretty close. And I'm going to back up a minute here. And first of all, when you decide what the deck height is, you have to know before where top dead center is on the motor. When that journal or that rod is at the maximum length of its stroke, or top dead center. And we've got a tool here that'll, it's real easy to make. This one's a little crude even, but it does the job. Why don't we put it in on these two, Bill? Grab the other two studs.
What we have here is a flat piece of aluminum stock, and it's got a screw tapped in it.
All we're really going to do is we're going to dead stop the piston a few degrees before top dead center, rotate it backwards until it stops again, and take notice. Take notice of the difference, and split that difference, and that'll tell us what top dead center is. We did it right. This might seem to be kind of a long, drawn-out process, but when you've gone to the expense of building a motor like this or investing in the parts, and you're going to set it up yourself, there's no sense in doing it so that it's wrong, or it doesn't give you the ultimate end result that you wanted to achieve with the engine.
So what we have here is this plate around here that's holding the barrel flush against the case,
right,
with some,
this just takes two spacers. You don't have to have this plate. I have this plate only because it doesn't let these spacers run down on the fins of the cylinders and break them off. You know, you spend $150 for pistons and cylinders and break the fins off of it. It's not a real good idea. Okay, now what we're going to do, we're going to crank this screw down a little bit. We're going to bring the motor up. The piston comes up and hits the screw, okay? Comes up and hits it, and on the front of our engine, we're going to look where the case half splits, and we're going to see just exactly how many degrees before top dead center that it's going to hit. Now, okay, it's hitting it right now at 8 degrees. Okay, and we're going to rotate this back all the way around the other way, and if everything's right, it's going to stop at 8 degrees again on the other side of top dead center. In this particular case, we're right on the money. So this crank, this tells us right now that the crank is in index and the pulley is correct to the crank. There's a possibility that through the manufacture of the crank or the pulley, it could be off 1 or 2 degrees, maybe even 3 or 4, but, you know, for what we're going to check, we want to make sure it's right. So we know that when we read top dead center on this pulley from here on out, it's going to be right.
Mm-hmm.
Okay?
So it's just a basic check you're making there.
It's a check. It's not, it doesn't have to be done, but it's a good idea. You know, if you're going to continue to build engines of this caliber, you know, these are simple things to make. There's no reason to, you know, get into extravagant, expensive equipment, but it's simple, makes the job a lot easier. What we're going to do right now is I'm going to come down and we're going to bring it around till it is right on top dead center. Okay. I'll buy that. That's top dead center. Now, I'm going to use a duck mic here. We'll see if it's zeroed correctly. It's good. And lay the mic or any checking device you have, bring it through the center line of the pin. Don't check it here or don't check it here. Check it right through the middle. The piston will rock in the cylinder a little bit and give you an incorrect reading. So that right through the middle, right dead in the middle of the piston, is where you want to check the deck. Okay? Or you can check it out at the edge, just to check consistency, or the fact that the pin is straight or the rod is straight. There's a couple other things you can check at the same time where it'll tell you if you find something out of whack with it. Okay, this is a depth mic. You don't ultimately have to have a depth mic to do it. You can do it with the veneer calipers and a straight edge. You know, it's not absolutely necessary. Okay, I'm going to do a couple places across the top of the piston just to see if everything's right. And so far, it hasn't moved at all. I'll turn and read the mic. About 63 thousandths. About closer to 65. Let's see. Let me check that again because I think I moved it. Six 68 thousandths deck height. So that's a lot of deck. That's more deck than we want to run in this motor. We want to run this deck at about 45 thousandths. That means the distance from the top of the piston to the top of the cylinder is going to be 45 thousandths. This is 68 thousandths, so we're going to subtract the difference between there from the bottom of the cylinder. But before we go any further,
23,000.
yeah, we're going to take 23 thousandths off the bottom of that cylinder. But before we do that, we're going to check all the other cylinders.
All four.
All four of them, just like we checked this one. At top dead center and dead stop it. Only because the journals on the crank could be out of index from the others. You don't want to go ahead and, you know, there's nothing you can do to correct it, especially if you've got a new crank and it's possible and there's no recourse on it. But we want to make sure that we check the deck at top dead center.
And I think we should probably bring into this right now, checking deck and what you want for a deck height. Dick had originally, earlier said 40 thousandths or 1 millimeter. That's fine. There are certain applications, certain type of cranks that are gonna need a little more deck. SPG rollers. Those rods stretch a little bit, the bearings and everything, they tend to need up to about 60 thousandths. Otherwise, the piston will hit the top, the head.
We'll say right now that we're talking about a plain bearing crank right now.
Right.
You know, I'm not
And-
even
Yeah.
getting into a roller crank.
Anybody using roller cranks
Not too
anymore?
much anymore. They're awfully expensive and rather frail. You know, people are using them in off-road racers, that don't see a lot of RPM or a lot of torque application. You know, I've seen a lot of failures of them that they get quite catastrophic when they break in the case.
Usually take a lot with them.
And there's not much
Cases,
left.
cams, pistons, and cylinders.
The plain bearing crank has really proved to be the most reliable, long life, it's a serviceable item. You have a roller crank and you lose a rod on it, what do you do with it? There's a few people on the west coast here that can repair it, but at a tremendous cost, and once they've been repaired, they're never quite the same as they were when they're new. So we don't push it. They're not good at all for drag racing. And if you had a high-speed car, let's say you were going to drive on the freeway forever, at 75 or 80 miles an hour, great, good crank. But for what we're doing, it's just not working.
What are we going to do next?
Well, we're going to go through and
Check all four.
yeah, well, we're going to check all four, and after we come up with an average, okay? Let's say we come up with a deck, a consistent 65 to 68 thousandths, okay? And we're going to take that average and correct it to an in-between, We may have one cylinder that's going to have 43 thousandths, one's going to have 45, maybe one's going to have 44. But that's so close that there's no reason to try to get it any closer. If you wanted to get it closer, set them all on the short side. In other words, set it all to the 43 thousandths, and you want 45. You'd have, let's say you have one cylinder is going to have 45, and the other three are going to have 43. We cut the top of the piston 3 thousandths, and then you'd have exactly the same deck. But you could start this thing up and run it, and shut it off and check the deck again, and you probably have a variance of a couple thousandths from that point on.
So what is after we check all four, what would be what are we going to aim for the deck on this particular engine?
45 thousandths is what I want on this motor.
Okay.
So I'm figuring the compression ratio in the head with that particular deck. That volume in the deck is used in calculating the compression ratio.
What would you say the maximum you could cut off the top of that particular piston?
That piston there, in this particular application, I wouldn't want to cut more than 5 or 6 thousandths off it, only because we need the top of that piston later on to be the thickness it is for the notch for the valve. Okay?
It's going to have a notch that's probably about 240 thousandths deep.
I see.
We need all the thickness we can get.
In the case of an engine that didn't need notching on the piston at all for valve clearance, you could run a piston 120 thousandths thick. In other words, you could take 100 thousandths off the top of the average piston and not hurt it in a way. But there's better ways to accommodate deck than cutting the top of the piston a lot. I don't like to do it. Okay, we're going to take this off.
Now you want to start out talking about what happens when you have a longer
And
stroke,
a longer
a
stroke.
78.4, or just a 78.
78 millimeter stroke,
By
and a Volkswagen rod.
Right.
This particular engine isn't the same one that we were dealing with over here. This has got a 78 stroke crank in it with a Volkswagen rod and a 90.5 piston and cylinder assembly, and the stroke dimension, or the pin to deck height dimension on the piston is still set for 69 stroke. So what does that leave us with? It leaves us with the piston sticking out of the top of the cylinder. Not a good way to leave the engine. Okay. What we have to do is measure how much the piston sticks out, and the difference between the top of the cylinder and the top of the piston, plus what we want for deck height. In this particular case, because we've got a Volkswagen rod, we're going to try to get 50 thousandths deck height in it. Where in this motor here we were looking for 45 thousandths. We're going to try to get 50 out of this. All right. we're going to measure from the top of this piston to the top of the cylinder. Take the depth mic again, but rather than spread the top of the cylinder like we did before, we're going to go over the edge of the piston, still through the center line of the pin. This way we don't end up dealing with this rock that's in the piston here on the pin in the cylinder. Okay, we leave it stick over. We bring the edge of the pin and the depth mic over to the side of the piston, and we come down and we come up with a measurement.
Which is what?
Okay, we did it right. We've already achieved our top dead center like we did before.
We should have 120 thousandths roughly there, huh?
Yeah,
120 thousandths, we're going to put, we want 50 thousandths deck.
50,000 deck, we put 170,000 spacer under it.
Makes sense.
Okay?
Mhm.
So, we're going to take this back off. We're going to slide this spacer that's under here. Let's show here, never trust what anybody tells you. If you've got a means of measuring it, check your spacer. We want 170,000 spacer. We've got a,
That's a dial caliper there.
yeah, it's a dial veneer caliper.
Mhm.
We've got 170,000.
That or a micrometer, either one.
You know?
Mhm.
Okay. We didn't get head, so we'll slide that
On the bottom of the cylinder.
spacer on the bottom of the cylinder. We'll slide it back over here, like so.
Dick, where do you get those spacers?
A lot of different places you can get them.
A lot of aftermarket shops
You can
sell
call,
them,
you can call here and order them. We can get them usually within 2 or 3 days.
What basically,
They have to be, if you've got a custom application, we can get a spacer made to any dimension. If you're building a very basic 74 by 88 engine, and in all theory, a 74 stroke motor needs 100,000 spacer under it to achieve the, the correct deck. You can order spacers that are already designed that way, but I don't like to do it because you're dealing with a case that might be a used case and might have been decked at one time or another. Rod length varies, stroke in the cranks vary, so you never really know for sure what you're going to have. And that's why we go to the trouble to check this, to be a little more
Are you going to use any kind of gasket?
No.
No gasket
No
at all?
gasket.
What
Never
kind of
use-
sealing material are you going to use?
In the case of the engine staying together for a long time, we'll use like 3M weather strip cement. We'll get a tube of it here in a minute. It's an adhesive.
Yeah, yellow
And
adhesive.
It's, yeah, there's a lot of other names for it. Yellow death, we do a lot of funny things with it. But put that on each side of the spacer, or the shim, and put the thing together. When you're going to assemble it, put that on only if you're going to torque the heads on. Don't put it on the night before and then the next day torque the heads on, because it will set up a little bit and take up some deck and eventually pound out, and you'll have some loose cylinders.
And getting back to the spacers. You can have spacers made anywhere in the country of Blanchard ground. Any machine shop that does Blanchard grinding is what it's called, can make spacers like this, because they can hold them flat and grind them, and it's a very accurate way of making them. These spacers we had made up for this motor after we had checked it.
It's kind of an oddball because it's a 78.4 millimeter stroke, common to Okrasa, and a few other crank manufacturers will come up with some oddball strokes. You get into some 76 millimeter strokes that just give you fits when you go to set deck on one of those. And, one way or other, you can accommodate the deck with the proper shim. Okay, we're gonna check the deck now. We've put the shim under it. We've got everything back together again. We're gonna check the top of the piston to the top of the cylinder. All right.
Right along in here.
We're gonna
So
put
it
the
doesn't
depth
rock.
mic back on it again, right to the center. We're going to crank down the old depth mic. And
Voila.
right there we got 49 thousandths. You know, I don't think they can see it on there, but it's 49 thousandths. We want 50 thousandths. I'd be satisfied with that, you know.
Great.
Okay. Go through and do the rest of your cylinders. You know, like I said before, don't trust this one that the rest are going to be right. Do all 4 of them. And one thing is if you do go into any machining of the cylinders, whatever you do, they all have to be the same. Don't let somebody say, well, you got 45 thousandths here and 50 thousandths here. We'll just cut 5 off of one of the cylinders. You'll end up with a big problem, you know. We have people come in with this thought in mind, and it doesn't work. You know, you end up with some leaky bases and leaky cylinder heads at the
Well,
same
you have
time.
to have the same height here to here on both
The
sides.
cylinders all have to be the same length. You know, so that's why if you're going to cut them all. Keep the engine uniform, you know, in its dimensions.
And make the difference between the two on the
On
top
the
of the
piston,
system.
you know, and, you know, get your averages. And deck is important. Too little deck, you'll hit the piston on the cylinder head in high RPM. And the deck gets real small, you can even create a detonation problem. You know, the air just can't get away from that distance at the base and the top of the cylinder head, and it actually statics the air and creates enough heat that it'll detonate. It'll create enough heat in the combustion chamber. So them Germans, they were pretty clever when they, you know, come up with that figure of 1 millimeter. You know, you shouldn't have less than 1 millimeter. And depending on the application, we like to see 45 to 50,000.
Good morning.
Put the cam on, we're going to degree it, and then we're going to talk about some...
We're going to talk about putting the cam gear on the cam and degreeing the cam in relationship to the crank.
We've already
Okay.
covered deck height, but there was something we forgot to tell everybody about deck height, didn't we?
Well,
About
we'll
marking
show
each
it. Yeah, in the midst of your deck height, you should mark each piston so that you know where it's going to go in later on. You know, you don't.
Cylinder.
You've gone to the trouble to make specific changes. You want it to be put back in that place again. Okay. This particular cam and cam gear, this is a straight cut gear against the bevel cut gear.
Here are the difference. There's the straight cut, and of course the normal radial cut there.
Yeah, okay, the difference here, this one's nice and quiet. In this particular engine, it's going to have a lot of valve spring, a lot of lift. It's going to try to push that bevel gear forward and backward in the case, which is going to wear this thrust bearing out. This cam gear won't do that. It's going to be just straight running off the crank gear. Okay, we're going to install this first off in a straight up position on the cam. Just the way the cam grinder designed it to be.
Tell them the difference in the washer.
Okay. There's 3 different washers that selectively go into these 3 recesses in the cam. One advances it, one retards it, and one is straight up. In other words, the cam is not in an advanced or retarded state. Now we're going to bolt this together here. The reason for degreeing this in the first place is that we want to make sure it's right. It could be as much as 4 or 5 degrees off of what the cam grinder intended it to be. And we're building this engine to such close tolerances, we want to be able to retain everything that's to our advantage. And drop it in there on its marks. Bring it down. Now, when you put the cam in like that, there should be clearance between these two gears. It's easy enough to check. The gear should rock a little bit. You can just about hear it. I'll bend down here. That's perfect. What you want to do is to check it in more than just one place. Rotate the engine around every couple of teeth on the gear and check it. And keep rotating it. Never just assume it's right in one place. Take it all the way around and check it. When you're satisfied that it's right, then go ahead and leave it there.
You should also, for your final check, torque the case halves together.
Yeah. The ultimate test is with the case halves torqued together. In this case here, we're just going to check it so that when we put the case halves together, we don't put it in a bind and find out we're in trouble. So what we're going to do here, we're going to take the other case half and put some lifters in it. Up here. We've already checked that the lifter's clear in the case. By the way, these are the handiest things anybody ever came up with for putting lifters in. When you're sliding the case halves on, nothing more aggravating, especially when you're setting an engine up. You don't want to be greasing everything up. You can just put them in there and it holds them up.
Yeah. They're just clip springs, and they're available from most all of the mail order houses, and many local parts stores have them too. They're lifter holders, just opposite springs. And they're very, very, very handy.
They make life bearable. We're going to torque this together, or pull it up tight. It doesn't have to be torqued together. We're going to install our dial indicator and our degree wheel on the front and our pointer. Pointer is very handy. It can be made out of a piece of wire, even. Bill, hold that up and show it to them. This is one we've made for using when we assemble an engine. Where it goes, hold it down here. Also, make sure you put the Woodruff key in. We tried it one night without that. It didn't work. It's kind of hard to decide where to put it.
And you're using a forged pulley here.
Yeah, that's
sand seal type pulley. This is just for your
That's
degreeing.
just for degreeing. I use that in here because I know it's consistent.
Yeah.
I know I can give a motor away, and I know that it was right off this pulley.
Yeah. Use the same pulley over and over. Just the standard.
Line it up on the Woodruff key.
Got the pulley on the motor with the Woodruff key. We've installed a little indicator here that lets us see exactly where the center of the case half is, so that we don't got to try to line it up down the center. Okay, we're going to turn the thing over now. I'm going to go through one revolution. Hang on them rods so they don't bang around. You can see here, it's come back to 0.
Major move.
Turn them up.
Wait a minute. Okay, now here we go. We're going to start watching the indicator come up, starting off 0, and it's going to come up to 50 thousandths. Bring it up to 50 thousandths, and then we're going to check on the pulley in relationship to the pointer we've got, and for the cam to be set straight up, it should be 36 degrees. What do you see there, Bill?
We have 34 degrees.
34 degrees, so it's 2 degrees retarded right now. We'll crank it through the rest of the cycle and count the number of revolutions. We've already gone by 1, 2, 3, 4, 16. Okay, that's what the card says it should have, is 416. That's the total lift at the cam. And later on we'll show you what the cam has for lift against what it gets multiplied in the rocker arm. In this particular one, it's going to multiply it up to 620 thousandths total lift at the valve. Okay, but we'll get into ratio rockers a little bit later. Okay, we're going to come back down again. And when we get to 50 thousandths again, we're going to check where the pointer is in relationship to the degree wheel to see if the valve is closing at the right time.
68 degrees.
68 degrees. So we're still 2 degrees off. So the cam is right on. We can bring that retarded situation into exactly what we want with these offset washers that can go right in the end of the cam. Bill will point to it. And put the cam gear in a little different place on the cam in order to make the cam timing be as that card says it should be. On an engine like this, because it's such a high performance cam and it's already got, the cam is designed to do what the grinder wanted it to do, I suggest setting it like the card says. Don't try to outguess these guys. They've been doing it a lot longer than we have. So, we'll go back down to 0 again, and we'll take it apart. We'll put a different washer in it and bring it up so that it's right what the card says. We'll take it apart here in a little bit and do that. The next thing we're going to do here, we've degreed the cam. Okay, we know the cam is where we want it. And as far as advance or retard, and in most cases I like to put a cam straight up. You know, it comes with a card like this from the cam manufacturer. It tells you what the cam is degreed at, where the intake valve opens, where it closes in degrees in relationship to the crankshaft, where the exhaust valve opens and closes in relationship to the cam, to the crank, and it tells the lift at the valve. And on the opposite side, it'll tell the lift at the cam. So we're going to use these numbers now to determine correct rocker arm geometry.
And most cam manufacturers will give you that information,
That
or you
cam,
should ask for it.
you should ask for it, or most reputable cam manufacturers will supply you with a card like this. You know, I haven't seen too many cams yet that didn't come without it. Okay? What we're going to do is we're going to put the cylinder head on. And what I've done, and it's for ease of operation and ease of turning the motor over by hand, is I've installed light springs. And these springs you can go to the hardware store and buy a real lightweight spring. Assemble the valve into the head with the retainer. In this case we're using a ratio rocker, which needs the use of a lash cap on the end of the valve. These valves happen to be titanium, and no matter what kind of rocker arm you use, you will use a lash cap there. But this will not apply as for just setting rocker arm geometry. But we're going to use a ratio rocker first, and you have to use a lash cap with a ratio rocker.
And that lightweight spring just is something to hold the valve on the seat.
Right.
So
It lets the cam, it lets the valve train track the cam. That's all. It's very lightweight, very easy to turn over. We're only going to use 2 valves for ease of explanation and showing what we're going to do. Ultimately, you should go through and check each valve with your adjustable push rod till you're satisfied that that's the length push rod you want. Okay? We're going to put the head on it here. Just slide it down over the cylinders. And in the case of not knowing whether we're going to have to notch pistons or anything like that, you can do this without the pistons in the engine. They're totally non-related to what we're going to do.
We're dealing with cam now.
We're dealing with the cam and push rod length and rocker arm geometry. Okay. And it's probably the one thing that's overlooked the most in the assembly of a high-performance engine. Okay? If everything bolts together and the valves adjust, a lot of times people are satisfied with that. But you can gain or lose maximum valve lift that's designed into the cam if the geometry is not correct. So we're going to show you how to do it. Okay? This, like I said, we're going to use a ratio rocker first. This rocker arm multiplies the lift of the cam 1.5 times. Okay? Whenever the cam lifts the lifter, in this case it's going to lift at 416 thousandths. It's going to multiply the lift at the valve by 1.5 times. It's going to end up with 630 thousandths approximately at the valve. Now the ratio in this rocker arm is 1.5. Okay? So we're going to multiply whatever the cam does by 1.5, and it's going to make the valve do that. Okay, we're going to stick the rocker arm on it now. These particular rocker arms are Gene Berg. They're, in my opinion, about the best you can get for the money. And the ease of installation, you buy them and bolt them on, and they won't give you too much trouble.
And strength-wise,
They're bulletproof. You know, you shouldn't have any trouble with them. They don't take any shim under the rocker arm on the stand. The boss, the stud here, they bolt right on in the stock location. No shim at all. Other rocker arms, if you use a Sig Urson rocker or an Autocraft rocker arm, Autocraft claims you don't need a shim under it. I've seen sometimes you do. A Sig Urson rocker, you're going to need a shim for sure. We'll go into what a Sig Urson needs a little bit later. Okay, we're going to slide the rocker arms on. First, let me back up a minute here. This is an adjustable push rod. Easy to make. You can make one out of a lot of different things. You can use a long bolt ground down, all thread rod is ground down on the end with an adjustment in the middle somehow. What I've done here is this is a 3/8 push rod on the top and a 5/16 on the bottom, and I've threaded the inside of the 3/8 to 8 millimeter 125, I think, and cut threads on the OD of this one the same. They screw together with a jam nut. You can make a number of different ends for this, and you'll have yourself a set of adjustable push rods that are very handy to have if you're going to do this more than once. I'm going to check the intake first. We'll crank the motor around, make sure that the lobe is down, like so. Slide the rocker arm shaft on. Find a hole here a little bit. Okay. Now, for all practical purposes, we're going to check everything at a lash that the engine's going to maintain when it's hot. In this particular case, this thing's going to run with about 15 thousandths valve lash when it's hot. So I'm going to take a 15 thousandths feeler gauge. I'm going to stick it in here. I'm going to adjust the valve to 15 thousandths, okay? You have to be careful because with the light spring you can overcome it and actually take away some of your lash. Run down the jam nut a little bit just so it doesn't get loose or change on you. Okay, now let's talk about geometry and what geometry is. In this particular case, what we're going to try to accomplish is a relationship between the stem of the valve, the center line, the pivot point of the rocker arm, and the push rod. Okay? Now, we don't want to push this valve from one direction the whole time. We want to start pushing it from the bottom side, work to the center, and get to the top. And at the center, you want that to be at half lift. And in this particular case, let's round it off. Let's say the valve's going to open 600 thousandths. At 300 thousandths, you're going to want your geometry to be That's the point you're going to check it. That's the only time you're going to know if it's right or not. And in the case of a high-lift rocker arm, this adjusting screw and the push rod are going to want to be in line with each other, straight through, just as if they were one solid piece going through, parallel to each other. When it's at total lift, the push rod's like this, it comes back at half lift, it's straight, and when the valve is closed, it's going to be, in that position. All right? If it's not what I just showed you, it's not correct.
Well,
Okay.
at half lift,
At half lift,
you want
you
this
want these things to be straight with each other. Okay?
straight through.
Now, the Gene Bird rocker arm is probably the easiest rocker arm to obtain correct geometry with, because he's taken the time to design the rocker arm correctly for the Volkswagen head. Okay? I'll go into the Sig-Urson rockers and what you have to do to try to correct what hasn't been designed into it. It's easy to do, and we'll cover it. Okay? Now, what we're going to do is we're going to put a dial indicator on the valve. Come down. And we're going to want to measure how much lift we've got. Okay? According to the cam card here.
This is fairly straight also.
Yeah. According to the cam card, this thing should have 635 thousandths approximately, saying that the ratio in the rocker arm is correct and the lift in the cam is correct as per the card. Okay? We're going to rotate this around. We're going to start rotating it, and we're going to watch for that indicator to move and the valve will start to open. Okay, there it goes. There's 100, 200, 300, 400, 5, 600, and 32 thousandths. And we're within a couple thousandths of what we want. It's satisfactory. Okay, now we're going to check geometry. We've noticed that as it goes through this sweeping curve here, that it's worked properly. Now the valve is closing. We're going to go back and close it all the way to 0. Taken with these light springs, sometimes you got to make sure that the retainer gets seated properly. Okay, we're going to start over again. But we saw that it had 630 thousandths lift. So we're going to take half of that. It's going to be 315 thousandths. We're going to crank the engine around, turn your crank or your pulley here until the valve starts to open again. Then we're going to go to 100, 200, 315. And we're going to check what we showed you before, right here. The straight line, just as if you were to intersect the line through the push rod, right through the adjusting screw. As Bill holds up this pointer here, you can see that we're straight with each other. That's what correct geometry is. If when you get to 315 thousandths and that thing is pointed this way or that way, it's not right. Okay? Now we're going to show you what you have to do to correct it. And we're going to just crank the motor through here. And there we go. Okay. In the case of the Gene Bird rocker, you're not going to have the problem because the relationship between the rocker arm and the boss on the head are correct. And if the valves are installed in the head in the correct height, there won't be a problem. Okay? In the case of an Urson rocker and the use of a lash cap, it may require putting a shim between the head and the rocker arm. Okay, I've got some shims over here, I think. Yeah, here we go. You can buy these in a little kit form from just about any VW performance shop, or you can send us and we'll send them to you. They're a little shim, and they go between the boss and the rocker. Here, Bill will hold up another head. They go right on here like this. between this boss and the rocker arm shaft. And what that does is it moves the shaft up into a range that it can sweep the foot of the valve with this shoe right here and correctly obtain the correct geometry. And every time you move this around, you have to change your push rod length. And that's why we've got an adjustable push rod here. When you finally obtain correct geometry, lock down your push rod, go on and check all the other valves. And if everything's consistent in your engine, the assembled height of the stem of the valve, the cylinder head surface from one to the other, then your push rod length should be the same all the way through. When you've obtained a good push rod length, lock your push rod down. You can buy a blank push rod like this. One of the ends isn't in it. See, it's got one end in it here and none in it there. You can take the push rod you've got here, use it as a guide, shorten this push rod accordingly, drive the end in it, and you've got yourself a push rod that's ready to go. In the case of this engine here, it's going to have dual springs on it. I recommend using 3/8 chromoly push rod. It's a large diameter, very strong push rod, and it'll withstand a tremendous amount of abuse in the form of a racing engine. Or even in the case of any dual spring, I recommend that push rod. Okay, let's pull this off and we'll show what happens with a stock rocker arm in the case of...
Now the lift on this rocker arm is, what was it again?
Well, the lift on the cam and the lift of the valve is 630 thousandths at the valve.
And the bird rocker.
This rocker arm, Bird makes two different types. He has a 1.45 and a 1.53.
And a stock rocker arm, a 1600 stock rocker arm is
1.1 to 1.
Yeah. A stock cam has 300 thousandths lift, multiplied through the 1.1 is 330 thousandths.
Mm-hmm.
So the cam is pushing the push rod up 300 thousandths, multiplies it through the rocker arm and open the valve 330 thousandths. It's just simple mathematics, and a lot of times the cam has to be designed to use the ratio rockers though. You just can't put ratio rockers on any cam. You can't go down and buy a cam that was designed to use a stock rocker arm and put ratio rockers on it, other than a stock cam. A stock cam will maintain itself with a ratio rocker, but that's the only one. Anything else, you get way too much lift and the duration is real short, and you end up with not a real smooth running engine. And sometimes there's not enough allowance in the stem, the guide bosses, and spring clearance, coil bind, things like that have to be checked.
How do I find out if the particular cam that...
It'll be marked. When you buy the cam, ask the cam grinder when you buy it, or the people you buy it from. They should be able to tell you, But 9 times out of 10, like in this case, this is an angle cam, and it tells you that this is to be used with a ratio rocker. It won't say it on the card, but it'll say it when you buy the cam.
I see.
It says to be used with a 1 point. Everything they've figured on that cam card is figured for a 1.5 ratio rocker arm. Okay, now what we're going to do here is we're going to take this stock rocker arm shaft and put it on this same head and show what we're going to have to do to achieve correct geometry on it. We've put the stock rocker arm on this to show you the difference and what to look for if you're not using a cam that's going to have a ratio rocker on it, how to look for getting correct geometry with the adjusting screw on this end. Okay, it's actually simpler this way than it is the other way, because the adjusting screw is easier to judge its angle to the valve than sometimes the adjusting screw on this end with the push rod. Okay? Now what we're going to do is we're going to crank it through. We've got the dial indicator set up like we did before. We're going to turn it through. This is going to have 460 thousandths lift at the valve through this 1.1 ratio rocker. Okay, so we'll crank it around, and there's 1, 2, 3, 4, about 465, okay? And we're going to come back, let it come back to 0. Then we're going to start over again, let it come back. We're going to go to about 333 thousandths. 330. There's 1, 2, 3, 30. Okay? Bill's going to hold up the pointer there. And you can see that the adjusting screw is pretty straight on with the valve. In this particular case, we could actually raise up the rocker arm shaft with a shim right there and shorten the push rod just a little bit. And I think we'd get even better geometry. Okay? Now, I'm not going to go through and do it because I want to go into the Urson rocker and show what happens there. But to get correct geometry, and a change has to be made, don't make big drastic changes, okay? Sit and analyze the problem if it's not right. You know, there is a solution to it. You know, if you can't see the solution, call somebody, you know. Call us, drop me a line, and we'll try to answer it for you. I'm sure somebody out there can answer it for you. Mm-hmm. You know, it is obtainable. And it's simple to do. And the smaller the cam, the less critical it can be. Okay? If you've got a cam that's got 380 thousandths lift, the rocker arm geometry isn't nearly as critical as a cam that has 600 thousandths or 500 thousandths. So there's kind of a breaking point as to its critical. Okay? And we're going to take this off. I'm going to crank this back up here. We're going to put the Urson rocker arm. This is a partially assembled Urson rocker arm here. We've put the Urson rocker arm on now, and we set the adjusting screw in about the middle of its travel. There's an oil slot in this adjusting screw, and you don't want to run it too far out one way or too far back the other way. You want to be able to have some adjustment, keep that adjusting screw close to the middle where it's supposed to be. Okay? Show them where there's the oiling slot in the hole. Oil travels up the push rod, through the adjusting screw, out a hole in the rocker arm, and oils the contact surface of the rocker arm on the shaft. Okay, now, we've got this bolted down. We're going to put the dial indicator back on it again. Things getting so used to being here, it's going to be part of the motor when we start it up. You'll never know it. Okay, we're going to crank this around. And we go 100, 200, 300, 400, 500, 620. Okay, this Urson rocker arm, its ratio is a 1.47 ratio. It's not a true 1.5 ratio. So it's not going to lift that valve as far as the Gene Bird did, which actually, in actuality on the cam, ends up being about a 1.5, about a true 1.5 ratio. So it's going to lift the valve further through its ratio than the Urson is. The Urson is a good rocker arm. We've used them on in fact, our race engine has Urson rocker arms on it right now. And I have very few problems with them to speak of. Down here, we've come up, we've got 620 thousandths lift. We're going to turn right around and come back to 0. And just like we did before, bring it around at 310 thousandths. We're going to try to have correct geometry. Here's 100, 200, 300, and 310. Okay, now we're right back over here to the adjusting screw on this end, and the geometry of it, the straight line we're going to intersect through the adjusting screw, right through the push rod, and there it is. It came out correct again. If it didn't come out correct, if at this point the rocker arm adjusting screw were leaning one way or the other, you would accommodate it with sometimes the length of the push rod and shims under the rocker arms. Okay, the first thing you want to do is put the smallest shim under the rocker arm, put it back together, compensate in the length of the push rod, and check it again. If it gets worse, then you know you went too far. You know, if it got better, you obviously made the right choice. There's no real rules in a Volkswagen that's had modifications to the cylinder head, because you've changed all the relative checking points. The valve stem height in the head, in a head that's had big valves installed in it, is not going to be what it used to be or what the factory set it up to be. You know, if the heads have been ported, competition valve jobs, things like this change the assembled height of the valve. So these things are going to change everything we do in the setup. That's why we're showing you the different places to check for correct geometry. Okay? We're going to bring it back around, let it go to full lift again. We're back up to 620. Come on back down here. And that's about the extent of rocker arm geometry. As we go through, we might find a few things that we might have even left out of here, and I'll try to bring them up so that, you know, we don't leave you sitting in the dark. You know, we'll talk about a few other things as we go through in a little bit that might help enlighten you in your rocker arm geometry too.
Fascinating, just fascinating.
Yeah, it's amazing these things will run at the RPM they do. You know.
As long as we remember the fact of the when it's at half lift, that it should be
half lift is the key.
Straight up in the half
That's
lift
the
is
key.
the key. Yeah.
You know.
At half lift, either your adjusting screw on a high lift will be in a straight line with the push rod. Or on a stock rocker arm, your adjusting screw will be in a straight line with the valve. At half lift.
If someone was doing this at home, they'd almost have to have a dial indicator, wouldn't they?
Not necessarily.
Okay.
You could get away with it. You could take a veneer caliper. It's a little more crude.
Run them down the side.
You know, you can measure the distance the valve travels that way. You know, that's the main reason. The dial indicator is nice to have. You know, if you're going to do a lot of this, you can buy one of these at Sears for a reasonable amount of money, and it's something you can have and use. Definitely get at least a 1-inch travel on a dial indicator.
Well, you can use a dial indicator all over the engine too.
You can use it for in-play, you can use it for deck height, you can use it for cam latch or cam lift, a number of different things.
Degreen the cam,
you'll use it, well, you know, you'll see, you know, we use it for degreeing the cam, and then, well, I think we're going to go into notching the piston. You can't determine how much notch you're going to need in the piston until you know the valve is going to open this far.
Okay, now we're going to go to the mill.
Yeah.
And we're going to be notching a piston.
Right. Well, first we're going to show how to mark the piston for a notch.
Describe
how to
it and
locate
mark.
the notch. That's probably the most important thing when you're going to notch your piston. And the guy at home isn't going to be able to notch his own piston. I can guarantee it. Okay? But he's going to have to mark them. And he's going to have to determine whether they're notched right when he gets them back. This is what we're going to show. Okay?
We're going to show how to mark it correctly so that when you do take it to a machine shop, they will be able to put the notch where you want it for your motor.
A lot of places will take and just say, send me your pistons, and they'll haphazardly notch them kind of by on a basic place on the piston. and that's incorrect on a Volkswagen. You take a set of cylinder heads like this with the welding that gets done to them, and the modifications and the guide location, everything changes enough. There's not 4 notches going to be exactly in the same place. Anybody that tells me they can notch a piston, 4 of them in a machine, and give them back to the person without having them scribed or marked, I can't see how they do it.
Well, especially on a motor like this, we don't want the notch being bigger or in the wrong location, because if it's in the wrong location, it's going to end up being bigger, or the valve's going to hit the piston, which is going to cut down. It's going to make the notch bigger, and it's going to cut down the compression ratio, because you're going to have a very big notch.
The compression ratio on a motor like this is very important, that you have what you want. And to achieve that, you want a uniform notch. You know, you have to know the volume of each notch. These have to be measured in cubic centimeters. And when we get done, we want to try to have as close to the same displacement in each notch as possible, so that we have the same compression ratio in each cylinder. You know, that's why we're going to be very exact as to how we mark them, how we notch them. We will CC them and measure it, and
Check them after we've notched them.
and we'll check them. We'll show you. You'll use the dial indicator to check the depth of the notch. We'll show how it's done. We'll actually, the engine will be set up just like this. We'll go through, and at a certain point on the degree wheel is where the valve's going to be closer to the piston, and we'll check it. We'll show that. We're going to take the cylinder head. We've glued the top of the piston, put it at top dead center, and we're going to slide the cylinder head on here. We bring it down like that. We drop a couple of washers on it. Just snug it up a little bit. Now, when you do this, you can do it at top dead center and get away with it. But by all rights, it should be done on the intake valve at between 5 and 10 degrees after top dead center, and the exhaust valve should be between 5 and 10 degrees before top dead center. Okay, so we're going to bring it around so that it's about 7 degrees after top dead center. Bill's going to hook the pointer up here so we can see a little closer. Okay, there we come to 7 degrees after top dead center. And over there, Bill, is my punch on the blue shelf there. It looks like that's what I need. This fits down the valve guide. You don't have the head assembled when this is done. You've got it exposed. There's no valves or springs or anything on it. The piston in that position on the intake, we drop this down the valve guide. You know what this tool is here. Every Ford garage has one. We put a mark. Okay, this has got a point on it. Anything with a point that fits down the valve guide. Okay. Next, we're going to take it and rotate it over here to 7.5 or so degrees before top dead center. We're going to go down the exhaust guide, another one of these, and hit it. Okay, that's the center of our valve and location on the piston. We'll take a scribe a little later and we'll scribe a mark on there just with a compass. The diameter, we want to cut a notch in there to clear the pistons. Okay, we're only going to do this one piston, and then we're going to check it. We're going to put light springs on the valves like we did when we did rocker arm geometry. We're going to bring it around to this position with a dial indicator on it, and that's going to check the clearance between the valve and the piston at this particular location. Okay? So
now, when you're building the engine, would you do one at a time like that? Is that what you're saying?
You'd assemble the whole thing to mark it But right now, I'm only going to do one. I don't want to cut 4 pistons
Okay.
wrong. I want to cut one, check it. If it needs more or needs better location, then we'll get that piston right, and we're satisfied. Then we'll duplicate. We'll go back and we'll mark the other 3 pistons.
And cut them the same
And
distance.
cut them the
they did
same
with the
distance
first
I
one.
did this one that was successful.
Then when you're done, you go back through and you check them all. You check them for clearance, and you check them for location.
Okay.
We'll take the head off here, now that we've made our punch marks. And just call me Butterfingers tonight.
Leave it.
And I'll emphasize that when we've made the mark with the punch, if you're going to send me the pistons or wherever you're going to send the pistons to have them scribed, just leave the punch mark and tell me what size valve you've got, or tell whoever's going to do this what size valve you're going to use. They'll do the rest. In this particular instance, we're going to have a 42 millimeter intake valve, and what we want to do, split the difference, that's 21 millimeters, and add a millimeter for, works better if I use these things in millimeters. We've got 21, we're going to add a millimeter for clearance, the radial clearance of the valve when it goes into the piston. On this particular engine, that valve is actually going to go down into that pocket. There's going to be that much lift at the valve. I'm going to set up this caliper here at 22 millimeters, which is going to give me a millimeter of clearance additionally. Put it in the mark we made, and just right around. If I do this like this, it'll work a little better. We just come right around, make a scribe mark, okay? We're going to turn right around. It's a 38 millimeter valve, that's 19 millimeters. We'll give it another millimeter radial clearance. We'll set this thing at 20 millimeters. We'll come right in here like this, and we'll scribe it. Now, like I said before, you don't have to do this unless you're going to notch your own pistons or have that facility.
Also, one thing that should be brought up now, when you're putting the pistons on the motor, now is the time to mark them as to their location. Number 1, number 2, number 3, and number 4. Because once they get notched, right and left, it does make a difference.
You can't mix them up. The intake notch is different than the exhaust. You don't want to end up having one in the wrong hole.
And you don't want a number 3 piston on a number 2 side, because it will make a difference.
Yeah. That's why we're going to this. Anybody that can notch a piston and give it to you right without doing this is a heck of a lot better than we are. I've never seen it done yet, where they're absolutely correct. This will be absolute. And we can run a lot closer tolerances in the engine and keep a better, a closer watch on even compression ratio throughout this engine.
Like you said, anybody can notch a piston. The notches will be real deep in comparison to what they need to be, which you lose cc's in the motor and you won't be able to get the compression ratio you want. This motor is going to be very critical because of the size. You're going to need the smallest notch possible, but yet it has to have the clearance.
That's about that. Next we'll go into showing you how that piston's notched and how to check it. We'll light spring it like we did with the geometry.
Mm-hmm. So we're going to go over to the
Piston
mill.
notcher.
Yeah, we'll go over to the milling machine where we've got an apparatus that goes in there, holds the piston, and we'll cut the notches and come back, and
we'll be able to see that. Okay.
we'll try to keep our fingers out of the hole mess too. And from here we'll go to the valve notcher, and we'll cut our notches. An engine like this engine is going to have about 14.5 to 1 compression. We're probably going to have to cut about 185 thousandths deep notch in that piston. And it seems like a lot, but it's better to have the clearance. You want to usually run between 60 to 80 thousandths piston to valve clearance. That is when that valve is in its closest relationship to the piston. You want to have that much clearance. Okay? Might not hit, but you want to have that in case the valve's going to valve float.
Why don't you explain a little bit about the procedure when you take it over to the milling machine? That's a beautiful new fixture you've made over there too, by the way. I have to congratulate you on that.
Oh, well, you know how it is.
Explain what that is on with the fixture you have there.
The fixture just holds the piston at 9.5 degrees, the same angle the valves are at in relationship to the head. Holds the piston at that number of degrees on the center line of the pin. And those marks that we scribed
earlier,
right here,
the cutter just goes right.
The cutters are designed, I had those cutters, I had my dad make those cutters for me, and they cut that notch right to a 42 millimeter notch and a 38 millimeter notch, just as we scribed it.
You did a gorgeous job.
And, well, the notch clears the valve. The notch is actually a little bigger than that, but it's fine. Anyway, we're going to set this back on now. The piston's back in, the cylinder's on. We've put our light springs. We can see the valves open up there. Light springs are on the head, so we can go through and check that piston to valve clearance now. We're going to run this down. We're going to mount our dial indicator back on it again. We already know our pulley's right. We've been through all that. Right in here, we're going to put the push rod in. Set the rocker arms on. Because we haven't made up our whole set of push rods, we can still use our adjustable push rod and do all our checking with that. We'll run it down. A little bit ahead of me there, but I'll pull it off like this. Okay, we've got the right amount of lash we're supposed to have. Now what we're going to do is we're going to rotate the engine around first of all, just to make sure that we do have clearance. I'm going to hang on to this rod. Nothing's hit anything yet. Okay, there we got 630 thousandths lift. We're coming back up. And there we are back to 0 again. Okay, now what we're going to do, the intake valve's closest position to the piston is going to be after top dead center. So we're going to come around here. The valve starts to open. Our timing mark here comes up. We're going to start at about 5 degrees after top dead center. I'm going to bring it around here. There's top dead center. There's 5 degrees after top dead center. Bill's going to zero the gauge, and this is going to tell us now, with the light spring, I can lift the valve off the lifter. You'll see how much clearance there actually is now between the piston and the valve. Right now we've got 30 thousandths clearance between the piston and the valve, the way it's set up. Now we don't know yet. We may have a place that's closer than that. So I'm going to move it 2.5 degrees further after top dead center, re-zero the gauge, and check it again. Okay, now we're down to 28 thousandths, so we're getting closer. We're not getting further away. I'm going to move it another 2.5 degrees. We're up to 10 degrees now. Okay, now we're back to 30. So we know that at 7.5 degrees was our closest point between that piston and valve. We've got 28 thousandths. That's not enough. We're going to take this piston now. We're going to cut an additional 35 to 40 thousandths in it. We're going to take the rest of them and cut them. Exactly the same. I'm going to take and go over here and we're going to check the exhaust valve. We're going to check it the same way, except for we check it before top dead center, not after top dead center. We'll check it, because this was consistent at 7.5, I'll check that one at 7.5 because of the way the cam is designed. Okay, now we'll just come back up here and you can take the, yeah. We'll pull this off of here. We'll just switch our push rod over to the...
Now you're going to do the exhaust.
We're going to do the exhaust. The exhaust is actually sometimes more critical. It sometimes takes more clearance or a deeper notch in the piston than the intake. It's also more critical because the piston encounters that valve in a different direction and can do actually more damage. In engines that we've seen in the past that have insufficient clearance and a valve's going to hit it, 9 times out of 10 it's the exhaust valve that hits because of the momentum of the system. Okay. Right now we're just going to crank it through and make sure that it doesn't come up and hit anything. Okay. The exhaust valve is going to encounter on the upward stroke of the piston. Okay. I'm going to set this at 7.5 because it was so consistent before on the intake, and we'll use that as our starting point. And we'll check it. Okay, and we did a good job on the exhaust. We've got 65 thousandths clearance. We're going to go and move it back to 5 degrees and see if it gets any closer. Nobody's perfect. The cam grinder might be a little bit off. Okay, now we're up to 75, so that's even better.
Well, you want to be careful not to have too much.
Right, you don't want to give up anything.
Yeah.
But 75 thousandths is ideal piston to valve clearance.
Okay.
For the exhaust valve.
For the exhaust
For the
valve.
exhaust valve. What's
Okay.
our ideal for the intake?
The intake I like to have about 60.
Okay.
You know, it varies depending the kind of spring you're going to run, the kind of valve you're going to use. A titanium valve, you can run less clearance. The valve is lighter, has less rebound on the spring, and they won't go into float quite as fast as a steel valve will. Okay, now I'm going to go up here to 10 degrees and have Bill zero that, and we'll check it. Okay, we're back to 65 again, so we know we're home safe right there. When I re-notch the intake here, I'll probably hit that exhaust about another 10 thousandths, and we'll be fine.
And if they have their pistons notched, they must do this.
They must check it.
They must check.
They must check it.
Yeah.
It can ruin $100 worth of stainless steel valves and $400 worth of titanium valves if it's not right.
And waste a heck of a lot of time.
A lot of time, you know.
Yeah. Miss the race.
Right.
Yeah.
Well, not only miss the race, you can. I'd miss the race for $400. And we'll take this off of here now, and we'll go back and we'll notch all the valves, assemble the motor up, complete. We've got our cam is dialed in, our deck is set, our case is clearanced. We've basically got a pump here that's ready to start making horsepower after it's assembled properly. We'll go through some of the basic things to watch out for on the assembly of an engine like this against a engine you drive back and forth to work. There's a few little things that would be different. I think the biggest thing to watch for in assembly is that cleanliness. You know, we started out talking about clean.
Yeah.
You can't have it too clean.
This is the clean room. You don't do any grinding in this room.
No.
You don't,
This
have
is-
any shavings on the floor in here.
Think you
Now,
can
if
do
there's
it, Bill?
anything you missed in anything we've done so far, if there's any particular thing, you just roll the tape back and go over it again until you get it absolutely clear in your mind and you're sure of the steps we've gone through. Some of the machining you've seen, of course, you're not going to be
Mark
able to do. So you're going to have to get Dick and Bill to do them, or you're going to have to find someone in the area that knows what they're doing, understands all these processes, and they're going to have to do it for you.
We're gonna try to let the guy understand what he's gonna build, why he's gonna build it, and not just be a bolt the carburetor on it and think he's got a hot rod Volkswagen. You know, what we want to say is the caliber of this engine is far beyond that of a progressive Holly and a Engel 110. Those are good things. They do add performance, but they're not what you call a race-worthy Volkswagen engine.
And it's also, if I might interject, and I see if you agree, it's also far beyond a case that's bored out, 92 slipped on it, and a cam put in it, and a Zenith slapped on it.
Right.
It's far beyond that.
Right. What we're trying to point out here in everything we do is a procedure that's going to gain the most out of everything you've done to it, starting from the choice of parts. You know, I think that if you're going to build an engine, sit down and decide what you want. You know, you're going to want a 69 stroke by 88 millimeter bore. You know, and will that serve your purpose? You know, that's the most economical way to build an engine. You can get away with a less expensive connecting rod, a less expensive crankshaft, no extensive case clearancing, things like this.
Yeah, and we dynoed your particular race engine the other day. Let's talk about that for a little bit, and we'll show everybody when we're dynoing it. Go ahead and tell us about that right now. Remember when we
Well, that particular engine is it's out of our race car, and it's a 1700 cc engine, or actually it's 1679 cc's.
It's a stock stroke.
It's a stock stroke engine. It's got a 69 stroke crank in it, and it's got 88 millimeter pistons and cylinders on it.
And look at the RPM we're getting out of this. Look at the horsepower.
It produced just a little over 200 horsepower, 204 to be exact, at 8,500 RPM.
Can you believe that? 200 and a little over 200 horsepower on a stock stroke Volkswagen motor. That's what we just saw, and maybe we'll see just a little bit more of it right now, and see the RPM that we can get out of this thing.
Yeah.
Look at that. Look at that RPM.
It kind of amazes you when you stop and think of how fast it's going around.
Yeah.
You know, just picture what revolutions per minute means.
You know, and it's so loud out there that we
Yeah.
even had to put earmuffs on the dog, didn't
Yeah, he doesn't like the noise.
we? Look at that.
Well, that also, the 8500 is just what we can run it on our dyno. It does produce horsepower farther than that,
It does.
but our dyno doesn't have enough water pressure to hold the RPM.
It'll make horsepower to around 9,700 RPM. I mean, it won't withstand it. You know, the water pressure that our property has here isn't sufficient enough to maintain it.
Well, I didn't mean to interrupt what you were saying.
Oh, no
I just
problem.
wanted to show everyone about that exciting dyno we did the other day. Please continue. You were talking.
Well, we were talking about what a basic hot rod Volkswagen motor would be, and in my opinion, it would be, for economic reasons, a 69 stroke with an 88 millimeter bore, or 90.5, or 90 millimeter NPR pistons and cylinders. These are efficient piston and cylinder combinations. You know, there are other bigger pistons and cylinders.
Well, you better clarify yourself then when you say 88 millimeters,
Okay, an
not
88
the slip-in 88.
No, not a slip-in 88. An 88 millimeter piston and cylinder that you have to bore the case and the cylinder head for. The only slip-in piston and cylinder that belongs in a Volkswagen is 85.5. Anything other than that belongs on the shelf
The
somewhere
cylinder
else.
walls are getting too thin.
But that particular combination, a 69 by 88 with the right cam and the right cylinder heads, is capable of making the average street car of around 1,600 pounds run in the neighborhood of 13 and a half seconds at around 100 miles an hour. And this is very respectable. You know, it would scare the death out of you on the street. You know, there's no reason to think that you have to have an 82 stroke or a 78 stroke to go that fast. Now, the longer the stroke gets in the motor, the more torque it can produce at a lower RPM, and you can make the car go faster, with no doubt about it. That same car with an 82 by 88 motor, which would be 2,000 cc's, with the same cam and same heads, would probably run 1250s, you know, with the right gearing in the same weight car. So I'm not putting down long stroke. I'm just saying, economically wise, this is the almost a better way to go, you know.
2180, 2180. That's all I hear everywhere I turn. 2180.
That's the magic number, I think. You know, it was for a long time. You know,
well,
there was
it's certainly
a day.
very inexpensive.
Yeah. You know, you can. The only thing is to buy a good 82 stroke crank, you're going to spend a lot of money today. You know, roller cranks are a thing of the past, in my opinion. You know,
They're very expensive and they don't last.
They won't last in a drag race car.
They won't last
You
on
know.
a street car either.
But the cylinder heads, the piston and cylinder choice, are two of the most important, along with the cam, choices that you can make in the idea behind hot rodding your Volkswagen. Those will give you the most performance gains for the least amount of money. You know, you'll spend a lot of money on your cylinder heads that have them done right, but you will definitely appreciate what you spent.
Yeah.
You know.
Do we want to talk about cylinder heads a little bit?
Yeah, we
Because,
can
we
point
took-
out a few things here.
Well, we took the camera down and we watched you mark the
lay out the combustion
lay out the
chamber.
combustion chamber and the intake ports, and we also watched you flow the head down there.
Yeah, we flowed a couple different cylinder heads.
Yeah, we can talk about that too a little bit later. But
We showed how we laid out the chamber.
yeah.
Now this particular cylinder head that's going on this engine is it's worthy of putting on the street. You know, it's just that the compression ratio would be too high. But when you
Can you see this in here? Can the camera come in and take a look at this right here? You think you can do that just a second? Okay.
okay,
And
this particular cylinder head, you don't really need this big a head on the street. It's not necessary. I think that you can get by with a smaller port and have something that is a little more drivable on the street.
You might also at this point, they're probably wondering why the valve seats look gold.
Okay, this is aluminum silicon bronze valve seats. We use these in a drag race engine primarily because they'll last a little longer. That's the
okay,
only
now
reason.
that's aluminum silicon bronze seats.
It's the same
very
material that valve guides are made out of.
Yes. Not
And-
just go some and just say put some bronze seats in there, because Toyotas use a different kind of bronze. And,
Yeah.
And it's very important that if you have someone slip in bronze seats, that
I don't recommend bronze seats for the street
Yeah.
at all. The expense would be the number one reason. A cylinder head for the street, cost-wise, anywhere from $500 to $900 is the price range you can look for. And not always is the most expensive going to get you the best cylinder head.
yeah.
You know, if you're looking for cylinder heads, and there's a lot of places that make them, you know, that will sell you a cylinder head. I think that when you're to that point and you're willing to spend that kind of money, talk to somebody that does it and is successful at it, not just pulls one off the shelf and hands you a ported cylinder head. This is a waste of time.
Well, a cylinder head that's going to work on your motor is a custom-made cylinder head, made for your combination. The cam you have, the displacement, and the carburation you're going to run, the weight of the car, that all makes a difference on getting the right cylinder head to get the most performance out of your car. Because the cylinder head is the one thing that's going to give you the most benefit out of a Volkswagen model.
That and the cam choice. Something else you might think about is when you're if you're going to buy a cylinder head, let's say, and you walk in and some guy says, I've got a cylinder head here I want to sell you. Find out what the compression ratio is in that head. You know, if he can't tell you, have him find out. Take it somewhere where they can measure the volume in here. They can tell you what the compression ratio is. If you've got a 82 by 88 engine and you put a head on there that was designed to have 10.5 to 1 compression on a 1700, and you're going to put it on this 2000 cc motor, all of a sudden you're going to have over 11.5 or 12 to 1 compression, which is something you can't live with on the street today. 9.5 on a dual carbureted motor is about the end of the line for a car on pump gas at 92 octane.
We not dynoed, we
Flow test.
we flowed this particular head. Explain, we're going to see a little bit of that flow that we did right now. Explain what this 12 inches of mercury is all about.
Okay, that 12 inches is your basis. Okay,
Your
that's your specific gravity for the test. All right, you could pick any number on this incline. This isn't the incline. This is the vertical manometer. Okay, but 12 is a good number to use.
Well, it's
a lot of
also-
people use it.
Well, it's a basis that we know.
We flow all our heads at 12.
So
yeah.
There's no rule that
It's a
says
reference point for you.
right. That's all it is
For
really.
your flow meter.
Okay.
And then the
Incline manometer. That's a comparison from an orifice behind the flow bench of the air going through it against the air going by the valve, and that's what gives us our reading on the manometer
And we open the valve 100,000
at a time.
for the lift that we've determined that
We
we're going to
duplicate the lift that the cam is going to have. You know, if I do you a set of cylinder heads, and you tell me you're going to put a FK89 in it, and it's going to have 630 thousandths total lift, I'm going to flow this head at 630 thousandths at increments of 100 thousandths. And sometimes, if I'm fine-tuning this area in the seat when I'm working the cylinder head, when I'm making it,
Yes.
I will flow it at 50 thousandths. Every 50 thousandths I'll make a change because it's a little more critical. The head is very sensitive in these areas to making better flow. And that's what it takes to get a good cylinder head and one that just has a 45-degree cut on there and a valve thrown in it. It's not going to work the same.
Now the reading that we got with this particular head on the incline, our final reading to
Was 11.9.
there it is,
And
11.9.
This head flowed extremely well for a 42 millimeter valve. A little later on, we'll show one of the new Superflow heads that Dean Lowry makes.
You want to show that now? You want
Yeah,
to
we can
talk
show
about
that. Yeah,
Okay.
and
We'll just go out and get one of those
Yeah.
heads now, and then we'll show what happened when we flowed that head.
right.
Okay.
Jerry's going to go out and get the other head. While he's gone, I'm going to bring up a fact here. This particular cylinder head is one that I made. This head complete in an all-out race situation. In other words, it's got titanium valves, aluminum silicon bronze seats, extensive modifications to the head in the area. You'll see here up close here the differences in the head, but this head is about a $1,600 cylinder head. Okay, the other head, the Superflow head that Bugpack is really behind and pushing right now, is a good head as a bolt-on item. But to make that head work to the degree that this head does, you will invest almost as much or more into that Superflow head. It doesn't come with a titanium valve. It doesn't come with any specific modifications to the point where it can flow like this head does right out of the box. Here he comes with it.
Here's the Superflow head right here. I don't know. Can you come in and take a look at this? This is a cast head that's been totally redesigned. Okay.
There was quite an article in Doom Buggies and Hot BWs on that head.
Now who makes this head?
Dean Lowry and Ken Lowry,
They make the head.
Dino Dinosaurs of years
Okay,
ago.
okay.
They make the head. They cast it and do all the machine work on it. Bugpack is real big right now in selling the head. You know, they've really done a campaign on it. And
That's a fine head.
it's a good head. There's not a thing in the world wrong with the head.
But now you've reworked this
Yeah,
head.
this head has been extensively reworked in the combustion chambers,
Can you see
in
that?
the port, the opening, the valve jobs. This head, to get to work as good as this head, which when I got done, it actually worked just a little bit better. On the second half of the flow, up through what we flowed them at the same number of lift, same inches of lift, this head flowed just a little bit better.
Okay, now this head, like this, is not out of the box.
No.
This is not out of the box.
Not
like
an
this.
out-of-the-box head, by no means.
Okay, let's look let's look at the flow bench now, and we're going to see this particular head bolted on.
Yeah.
And we're going to see our
We'll see it
reference
flow.
point of 12 again. And here's our incline.
Yeah, and you'll see it go up here. Right about here, after 300 thousandths, you'll start to see the head is starting to pick up a little bit of flow. Not by leaps and bounds, but a little bit. An increase is better than a decrease. And on the bottom, from 100 to 300 thousandths, it didn't flow quite as well as my head does. Okay, but the differences is not enough to worry about. They're not enough to give a reason to buy it or not to buy the head. You know, my biggest concern is that what's going to work best on the engine. If when we get to the point these go on an engine and they actually work better, then I'll even have more to say about them. But right now we haven't seen them on an engine. I've seen them on a few engines at the track, and I haven't been that impressed. Only because the cars they were on didn't go faster than they did with a conventional head.
I see.
But time will tell. You know, the more we work with something, the more we can make it work better. So
It's neat that someone
I think it's great.
that went out into the
You know,
trouble to
went to the trouble,
redesign this. Yeah.
and I'll point out the alloy and the design of this head is in my opinion better than a stock Volkswagen head.
Everything a stock head should have been, huh?
Yeah, in a few places a little more than it needs to be. The ports are in some cases a little bit too big, but for an all-out drag race situation, it's a good head. It's got a big port in it. But for the street, I don't think it's the answer. Because for about the money you'd spend on that out of the box, I can make a street head capable of making any size engine work to the maximum. Okay, if it's a 1700 or it's a 2-liter 82 by 88, any engine in there, a head can be designed to work on it for about the same money, and with not making any compromises at all. You know, and I might mention the fact that all these things we mentioned, and when I've mentioned an ET, an elapsed time of 13.5 seconds or 12.5 seconds, all these things are figured on the fact that the guy driving the car knows what he's doing, has done it more than once, and there's a little experience behind them. You know, you're not going to go out there, build a motor that's capable of going 13 seconds and have never driven it down the track and make it go 13 seconds. You know, it's not going to happen. So these are things to keep in mind, you know, when you're doing it.
More to the race than the motor.
Right, right. Make sure the car's safe too. Don't go out in a death trap and end up, you know, the other side of the guardrail. We've seen that happen too many times. We're gonna, in fact, I'll go through and show a whole thing here on how we've already showed you how to figure your deck, okay, or how to come up with how much deck you have. There's a formula for converting that into cubic centimeters. Take along with the cubic centimeters that are in this volume of the chamber here, and comparing it to the volume of the cylinder, you can calculate your compression ratio. There's a very simple formula for it. We'll go through and show you how to do it. You know, we'll show how this is measured. If you don't have a barrette, I don't recommend going out and buying one because you won't use it that much. I'm sure there's places around that can do it, you know, or you can send the heads and I can calculate it and correct it, change it if you want. You know, bring the compression ratio to whatever your heart desires. But like I said before, if you're going to drive it on the street, 9.5 to 1 for pump gas is about it. You know, you can buy better gas, but it can start getting awful expensive. This is a barrette. It's graduated in cubic centimeters, and there's 50 cubic centimeters in it. Okay, we're going to fill this with we fill it with solvent. You can fill it with water or alcohol, any liquid. And you know, this will remind you of your chemistry days back in junior high school. And we're going to fill it up to the top, and we're going to place the head under it with the valves. You can do this with the head apart even. Just grease the valves and drop them in on their seat. Put the spark plug in it. We have this plastic lid that we grease the face of the chamber. We lay it in like so with the valves in. Let me drop a valve in there, Bill. Let them see us exactly. The valves will be in like so. The spark plug will be in it. This will be greased and dropped in there. We'll fill this volume up with the liquid in here and measure it. Very simple. We'll take whatever we get for a reading there. Let's say we got 35 cc's. And we have, in the deck height of this motor at 50 thousandths, there's going to be 45 thousandths depth, which in cubic centimeters is 7.5 cubic centimeters in that much depth.
On an 88 bore.
On an 88 bore. Okay. The diameter of the bore will vary that dimension, but for what I'm going to say is that we've got 35 cc's here, we've got 7.5 cc's in the deck, and on a this particular motor there is 450 cc's in one cylinder. That's the cylinder volume. You'd add the total of those up, you'd come up with a total.
In this motor you also have notches. You
Okay,
have to
you don't confuse them right
well,
now. You'll take the total of all three of those volumes, the volume of the chamber, the volume of the deck, the volume of the cylinder, add it up, then take the total of the chamber, the total of the deck, and divide it into the total that you got of all of them, and it'll give you your compression ratio. All right?
static compression.
Yeah, static compression ratio. Once you've done that, if you go on to the next one, CC it, you know, we or anybody that does this for you, if they do it right, will CC all your chambers. The rest of the volumes are a known fact. You know, your deck height may vary 1 or 2 or 3 thousandths, but this isn't important. You know, it's not going to change it that much.
Yeah. So basically, we just wanted to show just a few of these, just to explain what CCing head is all about, just so you understand that.
A standard Volkswagen head, unfly cut, standard chamber, has approximately 50 cc's in it. So by diminishing those cc's, you increase the static compression ratio of the engine.
Mm-hmm. What do you mean by static compression ratio?
Static compression ratio is that as the thing sits here dead on the bench. And it's different than running compression ratio. When this thing is running at an idle, it might only have 5 or 6 to 1, maybe less, compression ratio, depending on the cam. The cam is the heart of the engine. It decides when the valves close in relationship to the position of the piston in the cylinder. And if the piston's halfway up the cylinder before the valve's closed, it's only going to compress what's left in the cylinder at that point. But the higher the RPM gets, this merry-go-round starts chasing, and all of a sudden, that compression ratio starts coming up. The stock engine got 7.7 to 1 compression, okay? This engine has got 14 to 1 compression, all right? Static compression ratio is the way it hangs here on the bench, you know, just what you see, all right? Running compression is different from that of static compression ratio. This thing at an idle only has probably 4 or 5 to 1 compression. All right. As the RPM comes up, this thing starts chasing itself. All right, and it gets into an advanced state. In order to keep everything happening in a realm which it can live with, the compression ratio starts getting greater. All right. So at 5 to 6,000 RPM, it starts reaching that compression ratio that we designed into it, you know, statically. All right. A stock engine, though, on the other hand, turns right around and does just the opposite through its cam design. That at lower RPM, at let's say 1,500 RPM, between 1,500 and 3,500 RPM, there's a curve in there in which the compression ratio reaches its peak. You see? And that's the difference between a stock engine and this engine here with a different cam. The cam is the heart. It decides how much air and fuel can enter that cylinder. And the cam timing in relationship to the piston timing can increase or decrease the amount in a different RPM range. That's why you say at 6,000 RPM it produced X amount of horsepower, and a stock engine at 4,000 produced X. Somewhere along the line, those two engines are going to create the same horsepower, but at a different RPM range. You know, one higher, one lower. And that's how we end up with it. I'm sure we've forgotten a million things. Here's one of your things you want to get and keep around. It's super weather strip adhesive. You can use that for sealing the base of the cylinders. Right around the base. Right around here. When you're dealing with stroker engines, anything with a long stroke, you're not going to be able to pull that paper gasket out of the gasket set and assemble the engine. So this is the stuff. It's yellow. They make it in a black, but don't use it. The yellow is what you want to get, and only put it on when you put the cylinders on and when you're going to torque the heads. Don't put it on the cylinders, stick the cylinders in the case, and wait for a week before you torque the heads. It doesn't work good that way.
And don't put your engine together with that either.
No, do not. I repeat, do not seal your case halves with this stuff. Don't put your oil pump in with it. Don't put your rear main seal in with it. This is a big no-no. Okay? The only thing this is to be used for is at the base of the cylinders. Okay, that or hold a rubber in your door or wherever else you might use one of them. This here is something we use and we like it very much. It comes with a brush. Get a close-up on that.
Take a look. It's a blue can. And it's when you buy it, it's practically impossible to get the top off. So you'll probably
They couldn't get it off. I got it off.
have to. Yeah, well,
On this one,
there it is. Okay. Anyway, this is very, very near, and it smells exactly like some stuff that we used to get from Germany.
Excuse me.
There you go. It's a Ford.
It's a Ford. I think I broke it.
Built tough to stay tough. Huh?
That's right.
Anyway,
Good stuff.
good stuff. You can use a lot of other things, gasket cinch, high tack. What else could you use?
Permatex.
Permatex. A lot of things you can use, a lot I don't recommend. You know, I personally recommend this. I'm sure there's a Ford dealer in your town. Go there and buy this. You'll be happy you did. You could do everything but put your cylinders on with it, you know. Okay, I'm going to let Bill talk to you a minute about ignition systems.
Yeah, let me get
He
out of the way.
understands them a little better, and
Let me scoot out of here.
let me trade
stay
places
there.
with him. He can go in there and
Okay, there's basically there's three types of ignition systems made for Volkswagens today. The most common is the point type, normal everyday, just like the one you have in your car. It doesn't have a vacuum advance, so on any kind of a high performance motor that you're doing, you're not going to need the vacuum advance. You're going to want a centrifugal advance. This is made by Bosch. It's a 009, probably the most common distributor on the market right now for a Volkswagen. There's another one it's made by Bosch. It comes out of Brazil. It's called the 050 Racing Distributor. It's almost identical in look, size, appearance, what it does, and the way it works as the 09. The curve is about 1 or 2 degrees different. It advances a little bit faster. But this is your cheapest, most economical, and in 90% of street cars and race cars, you will find one of these in it, as far as it'll serve the purpose. Then you get into higher racing applications.
Higher, anything over about 7,000 RPM.
You'll go. This here is a Stinger ignition. It's a magnetic pickup. Comes with a little box because everything gets it has a triggering device in here that goes to the box, and that's what controls the spark to the wires and everything else. This is what they call the electronic ignitions. This isn't a CD unit, it's just a magnetic pickup electronic ignition. The other one that you see a lot on racing Volkswagens, just about always on a drag race application, is a magneto. We don't have one here. They're getting phased out a little bit because of the cost. The magnetos are getting very, very expensive. Today you would have probably $350 to $400 in a magneto, where the Stinger ignition, which is probably the next best thing for
I
racing.
wouldn't say the next best.
Well,
I'd say it's better. We've used it at the same time, at the same track, within 10 minutes of each other as
a magneto.
And the car never went faster, it never went slower.
Right.
It was cheaper to buy.
Right.
It was less troublesome when installed properly, and had one advantage in the sense that we could install a retarding unit in our distributor that you couldn't do in a magneto.
They make their modules that hook onto this with retards built into them. We also put another set of pickups, a magnetic pickup in here, which placed in here at the right position was 5 degrees retarded, and we could manually retard the ignition when we wanted to. And this unit is approximately $250, so it's a little bit cheaper than the magnetos. Magnetos just keep getting more and more expensive. Your common 09 and 050 and other, point distributors run to anywhere from about $30 to $50, depending on what you're buying and where you're buying it.
Mm-hmm. In any case, I don't think this distributor can be beat
For a street application.
for a street application. If you're going to run that motor over 7,000 RPM, between 7 and up, and actually produce
Constantly.
horsepower at 7,500 and 8,500, that distributor will not work. There's not enough spring tension on the points. It'll go into point float, and nothing works at that point at all.
For you old timers, according to Bosch, this 009, this one here made in Brazil, by the way,
Yeah.
not coming out of Germany anymore. There's a few around yet, but according to Bosch, this is an exact copy of the old 010 distributor. According to Bosch, that's what they tell us. So for you old timers that say, well, I have an 010 and it might be better than that or whatever, according to Bosch, this is the same exact copy. The 010 was a mistake that Bosch made. It was a gigantic mistake, and they found a way to market it in Southern California by putting it in race cars. There's a long story connected with that. So don't be afraid to get an 009 and stop looking around for 010s. I still get people who come to me
gotta
and
have an
say, I
010.
gotta have an 010,
Yeah.
gotta have one, put things up in bulletin boards and everything. This is it right here.
If you have an 010 or the 019, they'll work just fine.
Sure.
Nothing wrong with them, but you can't get it anymore.
Right. They're not
Stop
readily
making it.
available. Parts for them are, if you do have them, you can still buy the
The
points
points and
condenser,
condenser.
cap and rotors.
But
you
they're
can't-
not. They're not any better, so don't think they are.
What have we missed?
I don't know. I'm sure we've missed a dozen things.
Now where did you hide the 92s?
There's no 92s here.
Why don't we all, on the count of 3, say "Boo 92," so that everybody gets
Gets the hint.
gets the message once and for all, because we've said it many, many times that we don't recommend 92s. All right, 1, 2, 3.
Boo 92. They're
Once and for all.
much too thin a cylinder wall. You know, they had their day. You know, they changed so much over the years too, from the time they were first introduced to the present, and people have got that stuck in their brain. They got to run 92s. You know, there's that magic number 2180. You know, the 92 piston, there was never anything wrong with it. You know, but they could never get it in a cylinder that stayed around, and that's why it didn't work. You know, had to have a puke can, a 5-gallon can in the back.
Well,
seat
you
to catch
also
the
heard
oil.
with the 92s is the racers would use them because that was big.
Yeah.
They could get more horsepower. And in a racing type, you don't run it very long or for very sustained. So it did last momentarily. It didn't last long enough, but it would last and it would make horsepower right out of the box.
Mm-hmm.
But after you've run it a few times, they'd start going away.
And I'm